What if reality isn't what you think it is? What if the world you see, the thoughts you think, even the space around you are just one version of something deeper, stranger, and far more mysterious? This isn't a dream, this is science, and tonight it's going to change how you see the universe and yourself. Welcome to 3 hours of mind-bending concepts that could redefine the universe. A slow, calm journey through the edges of physics, consciousness, and time itself. So before we begin, let us know in the comments, where in the world are you watching from, and what time is it for you right now? If you're someone who loves falling asleep to calm, intelligent content, or if you're just curious about how deep the rabbit hole goes, don't forget to subscribe. We make videos like this every week, and they only get stranger from here. Ready? Let's begin. Chapter 1. The Holographic Principle. Is the universe just a projection? Thus, what if everything you've ever touched, seen, or loved was just a hologram? Not a digital illusion, but a real, physical phenomenon projected from the edge of reality itself. This isn't science fiction. It's one of the most serious, most profound ideas ever to emerge from theoretical physics, the holographic principle. In a strange twist of logic and mathematics, some physicists believe our entire three-dimensional universe might be encoded on a distant two-dimensional boundary, like a cosmic movie, playing on the inner walls of reality. And if this principle is true, then the world you know isn't quite what it seems. It's not less real, but it's real in a very different way than you might think. To understand where this idea begins, we must first journey to the heart of one of physics' greatest paradoxes, the black hole information problem. Black holes, those mysterious, inescapable pits in space where gravity is so strong that not even light can escape, have long fascinated scientists. But when physicists tried to reconcile black holes with quantum theory, they found something disturbing. According to Stephen Hawking's groundbreaking work in the 1970s, black holes emit radiation, what we now call Hawking radiation. Over time, this radiation causes a black hole to evaporate, slowly losing mass and shrinking until eventually it disappears. But this presents a dilemma. If a black hole vanishes, what happens to the information about the matter that fell into it? According to quantum mechanics, information cannot be destroyed. It's a sacred law. Yet general relativity, the physics of black holes, seems to ignore this rule. If a black hole simply evaporates, then everything it consumed would be lost forever. That breaks quantum theory. This contradiction haunted physicists for decades, but in the late 1990s a radical solution emerged. One that didn't just resolve the paradox, but flipped our entire understanding of reality inside out. This is where the holographic principle takes center stage. The key insight came from string theory, a theoretical framework that tries to unify all fundamental forces by imagining that the smallest building blocks of reality aren't particles but tiny vibrating strings. In string theory, certain mathematical models suggest that what appears as a three-dimensional space can actually be described by a two-dimensional theory, as if the 3D world were projected from a flat surface. Imagine for a moment a hologram, like the kind you might find on a credit card or an old-fashioned novelty sticker. The hologram appears three-dimensional to the eye, but it's encoded entirely on a flat surface. The depth is an illusion, created by the way light interacts with the pattern. Now scale that idea up. What if our entire universe with its stars and galaxies and people and thoughts was also the result of such a projection, not an illusion? Exactly, but a 3D manifestation of information stored on a 2D boundary. This is the essence of the holographic principle. The most famous embodiment of this idea came from physicist Juan Maldacena, who in 1997 proposed what's known as the ADAS-CFT correspondence. This correspondence suggests a deep connection between a gravity-based theory in a five-dimensional space, specifically anti-de Sitter space, and a quantum field theory, without gravity on its four-dimensional boundary. In simple terms, the physics happening in a bulk volume of space can be completely described by information on its lower dimensional edge. That sounds abstract, and it is, but it shook the foundations of physics. For the first time, there was a concrete mathematical model that suggested gravity and space itself could emerge from a theory that didn't include them at all. This model was limited to a particular type of curved universe, one not quite like our own, but its implications were profound. If it holds true even in a broader context, it might mean that space is not fundamental. It might mean that what we perceive as distance and depth, as up and down and far and near, are just emergent properties, illusions created by deeper, more abstract relationships, encoded on a lower dimensional surface. In this view, Gravity isn't a force that operates in a pre-existing space. It's a product of information interacting on that lower dimensional screen. Just like temperature emerges from the random motion of molecules, space and gravity might emerge from quantum entanglement and information flow. This leads us to an even stranger possibility, that space itself is not real in the way we think. It's not the empty stage on which the play of matter and energy takes place. It's a construct, an emergent phenomenon created by something more fundamental. If that idea sounds too wild, consider this. Recent studies have suggested that even entanglement, the spooky connection between particles that Einstein famously hated, might be the glue that holds space together. In other words, the geometric structure of space might arise from how bits of information are entangled across the universe. This is mind-bending. It means that your position in space, the location of the Earth, the Moon, the stars, they're not fixed coordinates on a map. They're the result of entangled information on a hidden surface. And this brings us back to black holes. According to the holographic principle, all the information that falls into a black hole isn't lost. It's preserved on the black hole's event horizon, the boundary around it. Like a cosmic hard drive, the event horizon encodes everything that ever entered. This keeps quantum theory intact, and solves the information paradox, while simultaneously suggesting that reality itself might be written on the edges of space. If this is true for black holes, some physicists say, then maybe it's true for the universe as a whole. Maybe our cosmic boundary, whatever or wherever that may be, encodes the reality we experience inside. What does that mean for you sitting here now listening to this? It means that your body, your memories, your voice, your dreams, they could be the product of a vast informational code playing out inside a cosmic projection. It doesn't make them less real, but it does make them more mysterious. The holographic principle isn't just a cool theory, it's a shift in perspective, one that redefines what it means to be real. If space, time, and gravity can emerge from something else, then what else might emerge from this deeper layer? Could consciousness? Could identity? These are not settled questions. They lie at the bleeding edge of modern physics, where math dances with philosophy, and reality becomes slippery. No one has yet proven that the universe is a hologram, but no one has disproven it either. And as we continue to probe black holes, quantum fields, and the edges of space-time, we may yet find that the surface, the boundary, holds all the answers. One day, perhaps we'll look up at the night sky and realize we're not peering into infinite depth, but gazing across the interior of a projection, the inside of a cosmic masterpiece, written on a wall we can't see. And maybe, just maybe, the truth has always been written there, waiting to be decoded. Chapter 2. The Simulation Hypothesis. Are we living in code? Look around. The texture of your desk. The ticking clock. The quiet pull of gravity anchoring you to the earth. All of it feels unquestionably real. But what if it's not? What if everything, the atoms, the stars, even your memories, is part of a vast computational illusion? This is the unsettling possibility known as the simulation hypothesis. It doesn't claim the universe is fake. Rather, it proposes that the universe is real, just not in the way we assume. According to this hypothesis, our reality could be a high-fidelity simulation created by an advanced intelligence with rules and constraints that feel like physics because they are the rules of the simulation. This idea may sound like science fiction, the kind of thought experiment better suited to movies like The Matrix, but remarkably, it has been taken seriously by scientists, philosophers, and even tech billionaires. The reason isn't just philosophical curiosity, it's logic, cold, consistent, inescapable logic. In 2003, philosopher Nick Bostrom published a paper that formalized this idea into a trilemma, 3 logical possibilities, only one of which can be true. He argued that if advanced civilizations are capable of running ancestor simulations, that is, simulated versions of their own evolutionary history, then one of the following must be true. First, that most civilizations go extinct before developing such capabilities. Second, that advanced civilizations choose not to simulate their past. Or third, that simulations are common, and we are almost certainly inside one. Let that settle. If intelligent life routinely reaches a technological point where simulations of conscious beings are possible, and if they choose to run them, then the number of simulated minds will vastly outnumber biological ones. Statistically, it would be more likely that you are a simulated consciousness than an original one. Now ask yourself, how would you know if you were inside a simulation? Would there be a glitch, a repeating pattern, a flaw in the system? Surprisingly, some physicists have started looking for clues, patterns in cosmic radiation, digital-looking behavior in the laws of physics, even limitations in quantum behavior that mirror computational constraints. One of the most compelling clues comes from quantum mechanics itself. At the smallest scales, the universe behaves not continuously, but discretely. Energy comes in packets, quantized values that resemble the behavior of digital systems. Position, momentum, and even time seem to be governed by minimum units. This digital nature has led some researchers to speculate that the universe may operate like a cellular automaton, a kind of grid-based computational structure where complex behavior emerges from simple rules applied over time. In such systems, entire worlds can be simulated with breathtaking complexity. But it's not just the quantum world that's strange. There are hard physical limits to how much information can be stored in a given space. The Bekenstein bound, for example, tells us that the maximum amount of information that can exist in a region of space is proportional, not to its volume, but to its surface area. This again echoes the idea that the universe is not what it appears to be. It may not be a smooth, infinite continuum, but a finite, computable system with boundaries and constraints, just like a program running on a computer. Still, some argue, even if we're in a simulation, does it matter? Isn't our pain real? Our thoughts authentic? Our connections meaningful? The answer, in a strange way, is yes. A simulated consciousness may be just as real, just as valid, as a biological one, so long as the experience is internally consistent. Think of your dreams. When you're inside them, they feel real. Your brain constructs entire landscapes, people, and emotions from scratch. Only upon waking do you realize it was fabricated. Could life be a waking dream, one constructed not by your mind, but by a computational system beyond your reach? One version of the simulation theory proposes that this world was built to study us. Like scientists simulating weather or pandemics, advanced beings might be studying social behavior, historical branching paths, or consciousness itself. We might be unaware participants in a cosmic experiment, watched not by gods, but by grad students in a higher dimension. There's another possibility, more unsettling still. What if the simulation isn't for science, but for entertainment? What our triumphs, tragedies, wars and philosophies are the equivalent of a vast, interactive drama, watched by entities far removed from our comprehension. This sounds disturbing, but from a logical standpoint, it's not less plausible than a natural universe. In fact, as computational power grows, the ability to create detailed, conscious simulations becomes more inevitable. Even our own primitive video games now contain non-player characters with rudimentary decision-making. Given enough time, it seems all but certain that simulated minds will emerge, if they haven't already. Still, the simulation hypothesis has critics. Many argue it's unfalsifiable, that it can't be tested, and therefore isn't scientific. That may be true for now, but some physicists suggest otherwise. They are actively searching for digital artifacts, small glitches, or inconsistencies in the cosmic code that might hint at artificial origins. For example, if the speed of light is a universal constant, because it's a built-in processing limit, a maximum refresh rate, that could be a clue. If space is quantized like pixels, if time flows in discrete ticks like a CPU cycle, then perhaps we're looking not at nature but at code. Still, these clues are subtle. The simulation, if it exists, is extraordinarily sophisticated. It would need to simulate not only particles, but consciousness, the flow of time, the feeling of choice, the illusion of independence. It would require computational power far beyond anything we understand. So, who or what could build such a thing? Some imagine advanced civilizations, millions of years ahead of us. Others suggest that future humans might simulate their own past, creating ancestors like you and me, to study the roots of civilization. In either case, we become echoes, digital reflections of lives once lived. And still the question remains, does it matter? If your love is real, your suffering real, your thoughts meaningful, then what difference does the substrate make? Whether carbon-based or code-based, the experience remains. The simulation, if real, is your universe. You are no less real for being simulated. But there's one final wrinkle. If we're in a simulation, what happens when the simulation ends? Would we know? Would it flicker out like a dream? Would time stop? Or would we continue, unaware, unbothered, content in our illusion? Or perhaps the simulation never ends. Perhaps time loops, rewinds, resets. Perhaps déjà vu is not memory, but repetition. The system replaying data. Perhaps your choices matter, not to you alone, but to the observer. In the end, the The simulation hypothesis isn't about escapism. It's about challenging what we mean when we say something is real. Whether we're flesh and blood or ones and zeros, we experience beauty, sorrow, curiosity, and wonder. Those experiences, simulated or not, define what it means to be alive. And that, perhaps, is the greatest revelation of all. Even if we are digital ghosts in a cosmic machine, even if every thought is computed, every action pre-scripted, we still search for meaning, still love, still ask the question why. And sometimes the asking itself is the answer. Chapter 3: Quantum Immortality. Could you be the one who never dies? You've probably heard of the multiverse, the idea that there are countless versions of reality, each unfolding differently based on the choices we make and the randomness of quantum events. But what if you could never truly die in any of them? What if, from your point of view, you always continue, always survive, no matter what? This is the strange, chilling idea known as quantum immortality. To grasp this, we must take a deep breath and dive into one of the most mind-bending aspects of physics, quantum mechanics, specifically a controversial interpretation called the many worlds interpretation. It doesn't just change how we see atoms and particles, it alters our understanding of life, death, and the very flow of time. In quantum mechanics, particles don't have definite states until they're observed. Instead, they exist in a superposition, a blurry cloud of all possible outcomes, and an observation occurs. This superposition seems to collapse into a single outcome. The standard interpretation says the wave function collapses, and that's what we perceive. But the many worlds interpretation offers a radically different take. It says the wave function never collapses. Instead, every possible outcome happens in a separate, branching universe. When you flip a coin, in one world, it lands heads. In another, tails. When you choose a path, every path is taken somewhere. Reality constantly splits into a vast, branching tree of parallel outcomes. Now, combine this with the idea of subjective experience, that your consciousness only ever experiences one outcome, and suddenly, you get a very strange implication. Suppose you face a life or death event, something with a small but non-zero chance of survival, like a game of quantum Russian roulette. According to many worlds, there's a version of reality where you die, but also a version where you survive. And from your perspective, the one you actually experience, you always find yourself in the branch where you survive. Over and over, no matter how improbable. Even if the odds are astronomically small, as long as they're not zero, there is a branch where you live. That's quantum immortality. It's the idea that your consciousness is locked into an unbroken stream of experience where you never die, at least not from your own point of view. Everyone else may see you perish in their branch, but from your internal perspective, you simply continue. Now let that settle in. You, the experiencing self, might be riding a wave through infinite branches of the multiverse, avoiding death by slipping sideways into the next surviving version of yourself. Not because you're lucky, but because your subjective awareness can only exist in the branches where you are still alive. This is not science fiction. It's a real philosophical implication of the many worlds interpretation debated by physicists and philosophers alike. It's untestable because it concerns the nature of subjective continuity, not observable events, but that doesn't make it any less disturbing. To illustrate this, imagine a quantum experiment designed with a 1 in a million survival chance. In most universes, the subject dies, but in one rare branch, they live. According to quantum immortality, the subject would always find themselves in that rare branch. No matter how many times the experiment repeats, they never subjectively experience death. Over time, this has strange implications. As others grow old and fade, you, the unkillable observer, persist. Perhaps you age, perhaps you don't, but you're always there. You become increasingly isolated, surviving against all odds, slipping deeper and deeper into improbable realities, just to stay alive. This isn't a comforting kind of immortality. It's not peace or transcendence. It's survival through sheer probability, dragging your consciousness into more and more unlikely universes, a form of eternal continuity that may become stranger and more distorted with time. Could it be true? And if so, how would you know? The unsettling answer is, you wouldn't. You wouldn't feel immortal. You would just keep waking up. Every close call would seem miraculous, every escape a lucky break. But from your perspective, luck would never run out. You would always be the one who survived, while other branches, the ones where you didn't, fade from your awareness like dreams you'll never remember. There's a haunting beauty in that, and a deep philosophical dilemma. It forces us to ask, what is identity? Is your sense of self tied to one body and one world? Or is it a pattern of consciousness, skipping between realities, preserving a single unbroken line of memory and awareness? If quantum immortality holds true, then you, the listener, will never experience death. You may witness it around you. You may see friends, family, entire civilizations pass, but your thread of awareness would persist through illness, through accidents, through the ticking erosion of time. Always you continue. But here's the twist. Your surroundings may become increasingly strange, because with each life-threatening event you survive, the probability of your continued survival drops, unless of course reality becomes more and more bizarre to keep you alive. In time you might notice reality bending, people acting strangely, rules shifting, because the only worlds where you survive are the weirdest ones, the most improbable ones, the branches where the universe contorts itself to keep you breathing. This idea borders on the mystical, and yet it emerges from cold, logical extrapolation of one interpretation of quantum mechanics. There's no divine intervention, no soul floating outside the body, just the machinery of branching reality, selecting, again and again, the version of you that continues. It also redefines death. From your perspective, death isn't an event, it's an absence, a path you never take. Your consciousness skips like a stone, bouncing from one survival to the next, always onward, never still. But what happens in the end? Is there an end? Does entropy eventually win? Or does your mind spiral into increasingly surreal realities, clinging to existence in a cosmos that no longer makes sense? Some thinkers suggest that quantum immortality leads to an infinite conscious prison, a state where you survive forever, long after the world you knew is gone, a lonely awareness in a cold and alien multiverse. Others argue that consciousness itself must eventually dissolve, that some limit must exist, some point beyond which continuity breaks. We don't know. We may never know. Quantum immortality can't be tested, because you can't observe your own non-existence. You can only ever say, I'm still here. And yet the idea lingers, whispering at the edges of physics and philosophy. What if you never really die? What if the last heartbeat is not the end but a shift, a leap into another version of you, still breathing, still moving, still wondering? It's an idea that defies comfort. It shatters the illusion of finality, and in doing so, it asks us to reconsider everything we believe about life and death. Are you afraid of death, or are you already beyond it? Chapter 4. The Observer Effect. Can consciousness shape reality? What if the world doesn't exist until you look at it? What if your observation, your awareness brings reality into being? It sounds like philosophy, but in the strange world of quantum physics, this is not just a metaphor, it's a measurable, testable phenomenon, and it's known as the observer effect. At the heart of this mystery lies one of the most famous and unsettling experiments in all of science, the double-slit experiment. It's simple in setup, but its implications continue to baffle even the most brilliant physicists. Imagine a screen with two vertical slits, behind it, a blank wall that can detect particles. Now, you fire individual particles, say electrons, one at a time through the slits. What do you expect to see? If electrons behave like particles, they should pass through one slit or the other, creating two distinct clusters on the back wall. But that's not what happens. Instead, the electrons form an interference pattern, a series of alternating light and dark bands, as if they were waves interfering with each other. Somehow, each particle seems to pass through both slits at once, interfering with itself. It gets stranger. If you try to measure which slit the electron actually goes through, if you put a detector to observe the path, the interference pattern vanishes. The electron behaves like a particle again, going through one slit or the other, as if it knows it's being watched. This is the observer effect. The act of observation collapses the wave function, the mathematical description of all possible paths, into a single outcome. Reality changes depending on whether or not it is being observed. But what does it mean to observe? Is it a measuring device, a conscious mind, a mathematical threshold? The truth is, no one knows for sure, and that uncertainty opens the door to a deeper question, one that touches on the very fabric of consciousness. Could conscious awareness be fundamental to reality itself? Some interpretations of quantum mechanics suggest that consciousness plays a direct role in collapsing the wave function. This view, known as the consciousness causes collapse interpretation, argues that without a conscious observer, quantum systems remain in superposition, all possibilities existing at once. Under this view, the universe doesn't resolve itself into definite outcomes until observed by a mind. In a sense, consciousness becomes a participant in the creation of reality. You're not just watching the world unfold, you're helping it become. This idea has supporters and skeptics. It raises thorny questions about what qualifies as conscious. Does a mouse collapse a wave function? Does a tree? Does a machine? Still, experiments continue to show that the mere potential to know the outcome of a quantum event is enough to change it. It's not necessarily about a human eye looking. It's about whether information about the system exists at all, and somehow, that potential for knowledge affects the outcome. A pause. Take that in. Your awareness, your simple act of noticing, may alter the physical state of matter and energy. This isn't mysticism, it's physics. And while the deeper mechanism is still unknown, the effect is real, measurable, and reproducible. Some scientists and philosophers take this further. They propose that consciousness is not a product of the brain, but a fundamental property of the universe, like space, time, or mass. This view is known as panpsychism. Under panpsychism, consciousness pervades all matter, not in the sense of full self-awareness, but as a basic, irreducible aspect of reality. Just as atoms carry charge and spin, they may also carry a sliver of awareness, and complex systems like the human brain organize those slivers into full conscious experience. If this is true, then observation isn't just something that minds do, it's something the universe does, through everything, at every level, a constant act of becoming shaped by attention, entanglement, and feedback. And that might explain another strange phenomenon, the delayed choice quantum eraser. In this variation of the double-slit experiment, scientists found that decisions made after a particle passes through the slits can still affect how it behaved beforehand. The future seems to reach back and reshape the past, depending on whether information is known or not. This calls into question our very understanding of time, and it reinforces a deep, unsettling idea that reality is not fixed. It's probabilistic, and consciousness might be the key to turning possibility into fact. What does this mean for you? It means that your presence, your awareness, may be woven into the very fabric of the cosmos. You are not an isolated mind, floating in a passive universe. You are an active participant in the unfolding of existence. It's not just a poetic idea. If observation determines reality at the quantum level, then the structure of matter, the flow of energy, even the passage of time might all be influenced subtly, mysteriously, by conscious experience. Of course, not everyone agrees. Many physicists argue that the observer effect is simply a matter of measurement, not consciousness, that it's about physical interactions, not subjective minds. And they may be right, but the mystery remains. Something about observation changes the outcome, and whether that something is mechanical, informational, or mental, we don't yet know. Perhaps consciousness is a lens, not a creator of reality, but a filter through which reality resolves into clarity. Without the lens, the world stays blurry, undefined, full of potential. With it, things come into focus. Or maybe consciousness is the light itself, not just revealing reality, but giving it form. In either case, the observer effect forces us to reconsider our place in the cosmos. We are not detached spectators. We are embedded observers, lenses, lights, participants in the ongoing construction of reality. And as we continue to study the quantum world, we may find that the answers to the deepest questions in physics are not out there in the stars, but right here in the act of looking. Chapter 5. The Boltzmann Brain Problem. Are you just a fluke of entropy? Right now, you feel grounded in reality. You have memories. You can look around and see a coherent world. Maybe you're even relaxing in bed, drifting off while this plays in the background. But what if none of it is real? What if you, your body, your thoughts, your history, spontaneously formed from chaos a few seconds ago? This is not a joke. It's a serious idea in cosmology, and it's known as the Boltzmann Brain Problem. It's an unsettling, bizarre consequence of entropy, time, and statistical probability, and it forces us to confront a very uncomfortable question. What's more likely, a universe as complex as ours, evolving slowly over billions of years, or just you floating in a void with false memories and fabricated senses, forming by random chance? To understand where this idea comes from, we need to talk about entropy, the measure of disorder in a system. According to the second law of thermodynamics, entropy always increases. Left alone, systems move toward chaos. Ice melts, buildings decay, Stars burn out. The universe began in an incredibly low entropy state, highly ordered, incredibly dense, and extremely hot. Over time it has expanded and cooled, with entropy increasing. This is the arrow of time, the reason we remember the past, but not the future. But here's the twist. In statistical mechanics, if you wait long enough, even a high-entropy system will occasionally produce a local fluctuation, a tiny pocket where order arises from chaos, like a swirling eddy in a still pond. Complexity can briefly emerge before dissolving back into disorder. The physicist named Ludwig Boltzmann explored this idea in the 19th century. He suggested that if the universe is eternal and governed by thermodynamic laws, then occasionally, very rarely, it will produce fluctuations. And one of those fluctuations could be a low-entropy region, like our observable universe. That doesn't sound too bad, but here's the problem. Forming an entire universe like ours is incredibly unlikely. It requires a massive, coordinated drop in entropy. Far more likely, infinitely more likely, is that a single observer spontaneously forms out of chaos, a Boltzmann brain. A Boltzmann brain is a self-aware entity, like you, that pops into existence through a quantum or thermodynamic fluctuation, complete with false memories, a false sense of place, and the illusion of history, and then vanishes back into entropy a moment later. From a probability standpoint, it's far more likely that one brain forms randomly than that an entire universe does. If this logic holds, then most observers in the universe would not be evolved beings in a structured cosmos. They would be isolated, fleeting consciousnesses, alone in the void. And now comes the disturbing question: how do you know you're not one of them? How do you know your past is real, that your childhood actually happened, that the room you're in exists beyond your own awareness? If Boltzmann brains are the most statistically likely form of observer, then odds are you are one. This is the Boltzmann brain paradox, and it strikes at the heart of scientific reasoning, because if we can't trust our memories or the stability of our environment, then all observations, all knowledge becomes suspect. You might think, but I see a consistent world around me, I interact with it. That's true, but a Boltzmann brain would think the same thing. Its illusion would be perfect. It would feel time passing, recall a life lived, experience thoughts and emotions, all fabricated in a flash of cosmic noise. So how do scientists respond to this? The paradox is taken seriously enough that many cosmological models are rejected specifically because they would produce too many Boltzmann brains. The theory predicts a future in which the majority of observers are these random fluctuations. It's considered unacceptable, even if the math checks out. In essence, we use our own existence, our belief in a stable, coherent past, as a filter to reject otherwise possible universes. We assume we are not Boltzmann brains, and we reject any model that suggests we probably are. This seems reasonable, but it raises deeper issues. Can we really use our own intuitions to define what's reasonable? What if the universe simply is absurd? What if our desire for logic, continuity and meaning is itself part of the illusion? One way to escape the Boltzmann brain problem is to assume the universe is finite in duration, that it won't last forever. If entropy eventually reaches a final unchanging state, heat death, then there won't be infinite time for random fluctuations. The odds of Boltzmann brains arising become negligible. Another possibility is that our understanding of entropy in quantum mechanics is incomplete, that in the deeper laws of reality, these random fluctuations are forbidden or suppressed. But until we know more, the question lingers. You may feel real, you may remember a life, but so would a brain that popped into existence 10 seconds ago, fully formed, fully convinced, fully alone. And maybe that's all you are. A brief flicker of thought in a vast, silent void, one coherent pattern of neurons, sparking once before fading. Or maybe not. Maybe you're part of a long, evolving continuum, a true history, shaped by stars and atoms and DNA. Maybe the universe did begin with a low-entropy bang, and you are the echo of that cosmic unfolding. Or maybe the truth lies somewhere between. Maybe consciousness, memory and matter all emerge from patterns we don't yet understand. Patterns that transcend randomness even in an entropic sea. The Boltzmann brain paradox doesn't answer these questions, it simply asks them, with a cold, mathematical clarity that leaves no room for comfort. And maybe that's the most mind-bending part of all. That science, in its pursuit of truth, can lead us not to certainty, but to the edge of what minds can bear. Chapter 6. The heat, death of the universe. When time itself stops, what happens at the end of everything? Not just the end of your life or the planet or the stars, but the end of time itself, the moment when the universe falls silent, forever. This is not the apocalypse of religion, or the cosmic bang of creation. It's something colder, quieter, and far more final. It's called the heat death of the universe, and it may be the most chilling idea in all of cosmology. To understand it, we have to talk about entropy again, the ever-rising measure of disorder. As the universe expands, it spreads out its energy, systems lose structure, temperature differences fade, stars burn their fuel, and eventually everything runs down. Energy becomes evenly distributed. No more contrast, no more work can be done. This is heat death, a state of maximum entropy where the universe reaches thermodynamic equilibrium. Everything is the same temperature, no gradients, no motion, no life, no thought, just an endless, unchanging sameness, cold, dark, and still. You might imagine it as a kind of cosmic graveyard, but that's not quite right. It's not destruction, it's exhaustion. The universe doesn't crash, it simply fades. Right now, the universe is still active. Stars shine. Galaxies collide. Black holes form and feed. But this activity is temporary. It's all driven by energy imbalances, the difference between hot and cold, mass and vacuum, matter and radiation. As entropy increases, these differences disappear. Eventually stars will exhaust their hydrogen and die. The brightest giants will collapse into black holes. Smaller stars will cool into black dwarfs. Planets will be torn apart by tidal forces or swallowed by red giants. Galaxies will drift apart as space expands. After billions and trillions of years, even black holes will evaporate, slowly leaking Hawking radiation until they vanish. What remains is a thin, cold fog of particles, spread across an ever-expanding moat. At that point, heat death begins in earnest. There's no energy left to power anything. No chemical reactions, no stars, no movement, no time in the way we understand it. Because time, as we experience it, is the unfolding of change. And here, there is nothing left to change. This is not a myth or a metaphor. It is a real scientific prediction. The most likely fate of the universe according to current models of physics. And it's terrifying in its simplicity. We're used to dramatic endings, explosions, collapses, bangs, but the universe, it seems, may end not with a crash, but with a whisper, or more precisely with no sound at all. Heat death is the ultimate entropy, a state where the universe's energy is so evenly distributed that nothing can happen. There is no structure, no contrast, no memory, no possibility for interaction. Everything is reduced to a uniform haze. And this raises disturbing questions. What happens to consciousness in such a universe? Could anything survive? Could thought persist without energy? The answer appears to be no. Thought requires energy flow, the movement of information. In heat death, that movement stops. There is no more thinking, no more being, just stillness. Even the concept of before and after dissolves, with no clocks, no events, no changes. Time itself becomes meaningless. It doesn't stop, it just ceases to apply. This isn't just a cold ending, it's a deep erasure, a final smoothing out of everything that ever happened. No history remains, no observer, no difference between here and there, just uniform emptiness, stretching on without direction or duration. And yet, this vision of heat death is not depressing to all. Some find in it a strange kind of beauty, a cosmic stillness that represents ultimate balance, a universe at peace, free from violence, suffering or struggle. But for many, it's hard to imagine a more complete form of oblivion. It doesn't just erase life, it erases potential, possibility. It removes the very conditions required for anything to happen, ever again. Still, there are alternative ideas. Some cosmologists believe the universe might not reach heat death. If dark energy, the mysterious force accelerating cosmic expansion, changes over time, it might eventually reverse the expansion. The universe could collapse in a big crunch, a fiery implosion, or it might rip itself apart in a big rip, where expansion becomes so extreme that even atoms are torn asunder. But if dark energy remains constant and no unknown physics intervenes, then heat death remains the most accepted model. It's a timeline that stretches unimaginably far ahead, 10 to the power of 100 years or more. That's a 1 followed by 100 zeros, far beyond the lifespan of any star, any galaxy, or any human imagination. And yet, for all its distance, the thought of heat death brings our own lives into focus. It reminds us that our universe is a temporary phenomenon, a brief structure rising from the sea of entropy, sparkling for a while, then sinking back into silence. In that sense, everything we are, every emotion, every poem, every discovery, is a ripple in a finite moment, a flicker of complexity before the return to equilibrium. Does that make our lives meaningless, or infinitely precious? After all, we are the rare result of low entropy. We are organized matter that can observe itself and contemplate its fate. That alone makes our existence miraculous, not despite the heat death, but because of it. The universe may end, but for now, it moves, it pulses with energy, it gives rise to stars, minds, and questions. And while that lasts, there is wonder. Heat death is coming, perhaps, but we are alive now, listening, thinking, dreaming. And in a universe that trends towards stillness, the fact that we move at all is extraordinary. Chapter 7: The Holographic Mind. Is memory stored in space itself? What if your mind isn't inside your head? What if memory doesn't live in your brain, but instead is woven into space itself? It sounds impossible, even mystical, but in recent years a growing number of scientists and thinkers have begun to explore a provocative idea that consciousness and memory might not be confined to the brain, but might emerge from a deeper structure, one that resembles the very fabric of the universe. Some call it the holographic mind. To understand where this comes from, we need to take a step back, not just into neuroscience but into physics. Remember the holographic principle we explored in Chapter 1, the idea that all the information in a three-dimensional region of space can be encoded on a two-dimensional surface? That space itself may not be as deep as it appears. Now apply that concept to consciousness. What if your thoughts, feelings, memories, all the intricate structure of your mind, aren't just chemical interactions inside a brain, but emergent patterns projected from a deeper, more fundamental layer? This hypothesis doesn't deny biology. The brain remains the most complex object we know of. Neurons fire, synapses strengthen and weaken. Patterns form, but what if the brain isn't the source of consciousness, but a receiver, a transducer, a local processor of a much larger, more distributed field? This leads us into the world of holonomic brain theory, a model developed by neuroscientist Carl Pribram and quantum physicist David Bohm. They propose that the brain processes information not like a computer, storing data in fixed places, but like a hologram, where information is distributed throughout the system. In a hologram, each part contains a representation of the whole. Cut it in half, and each half still holds the entire image, just with lower resolution. Pribram noticed that the brain behaves similarly. Memories don't seem to reside in specific locations, but appear to be distributed, emerging from interference patterns across large areas. That's where the connection to holography comes in. If the brain stores data as interference patterns, then our thoughts, memories, and perceptions might operate much like a hologram, constantly updating, reconstructing, and projecting reality. This model could explain some puzzling features of memory. For example, how people can retain coherent memories even after parts of their brain are damaged, or how memory recall feels more like reconstruction than playback, a dynamic reassembly of fragments, not a simple replay of stored footage. Now imagine this concept expanded beyond biology, to space itself. Could the universe function like a cosmic hologram? Could consciousness arise from the interference of deeper fields, patterns embedded not just in neurons but in the very geometry of space-time? Here, the boundary between mind and cosmos begins to blur, and we are drawn into a different kind of physics, one where information is more fundamental than matter, where fields and structure, not particles, give rise to experience. If memory is a distributed interference pattern, if the mind is non-local, then perhaps consciousness isn't bound by the skull. It might emerge wherever complex structure exists, in the brain, yes, but potentially also in systems we don't yet understand, stars, networks. This view resonates with the holographic universe idea, where the three-dimensional reality we experience is a projection from a two-dimensional boundary. If space and time themselves are emergent properties, then perhaps so is the mind, and perhaps they emerge together. This might explain some deep philosophical intuitions, why humans have always sensed a strange connection between the self and the cosmos, why meditative states sometimes dissolve the sense of separateness, why memory feels spatial, not linear, why we sometimes experience insights that seem to come from nowhere. It's not a mystical claim, it's a scientific possibility that consciousness is an emergent pattern, encoded in the holographic structure of the universe, and the brain is the interface, a local translator, not the originator. That also reframes death. If consciousness is distributed, if memory and awareness are not stored in a fixed location, then perhaps the end of brain function does not immediately erase the pattern. Perhaps the pattern persists, diffused, embedded in space-time like ripples in a pond long after the pebble has sunk. This is not to say that individual identity survives death, but it suggests that consciousness may be less about individual storage, and more about participation in a larger verse, a shared structure, a pattern that reappears, not by design, but by the logic of the universe itself. There is still no proof. These are models, ideas, not confirmed science. The brain is still essential. Neuroscience remains grounded in biology, but more and more researchers are beginning to ask, what if the brain is not a container, but a conduit? This leads to another question. Can memory be stored outside the body? Experiments in quantum cognition and extended mind theory suggest that thought might not be as internal as we think. Some research hints that attention and intention might influence systems beyond the body. And memory retrieval may involve entangled processes, not just biochemical states. Even if controversial, these ideas point to one thing. Our current model of the mind may be incomplete. We think of memory as linear, stored like books in a mental library, but maybe memory is spatial. Maybe it exists in patterns. Maybe the act of remembering is not pulling data from a shelf, but tuning into a frequency, like a radio receiving a signal. And if that's true, then space itself becomes the library, and your awareness, are the reader. This vision of the holographic mind doesn't diminish the brain, it reveals its elegance. As a decoder, an amplifier of deeper structures, it invites us to think, not just with our heads but through the universe, to see ourselves as part of a system so vast and intricate that our very thoughts are ripples in a cosmic sea. You are not just in the universe is in you, encoded, interfering, remembering. Chapter 8. Retrocausality. Can the future affect the past? Time feels like a one-way road. We wake up, we move through the day, the past grows larger behind us, and the future stretches ahead like an empty sky. Cause comes before effect. Action leads to consequence. That's how the world works. Also we believe. But what if it doesn't? What if the future can reach back and shape the past? This is the strange idea known as retrocausality, the possibility that effects might not just follow causes, but precede them. It sounds like science fiction or a philosophical thought experiment, but retrocausality is not a fantasy. It is a serious topic in the foundations of quantum mechanics, one that challenges everything we think we know about time. The seeds of this idea lie in experiments like the delayed choice quantum eraser and the entanglement paradox, which seem to show that decisions made in the present can influence outcomes in the past, or at least change what appears to have happened. Let's begin with a version of the famous double-slit experiment. You send a single photon toward a barrier with two slits, behind which is a detection screen. If you don't measure which slit the photon goes through, it creates an interference pattern, behaving like a wave, as if it passed through both slits simultaneously. But if you measure which slit it went through, even indirectly, the interference disappears. The photon acts like a particle. Observation collapses the wave of probability into a single path. Now add a twist. In the delayed choice version, you decide whether or not to measure the path after the photon has passed through the slits, but before it hits the screen. Amazingly, the photon seems to retroactively change its behavior based on your decision, as if it knew in advance whether it would be observed. Even more bizarre, in the quantum eraser experiment, you can erase or preserve which path information after the detection occurs. The interference pattern appears or disappears depending on whether the information exists, even though the detection already happened. This leads to a deep question: are we witnessing retrocausality, the future influencing the past? Or are we misunderstanding what time really is? Some physicists believe that these experiments hint at a time-symmetric reality, where events are not strictly ordered, but interwoven. In this view, cause and effect are bidirectional. The universe doesn't unfold like a movie reel, but like a web, where connections run in all directions. One interpretation that embraces retrocausality is the two-state vector formalism proposed by Yevgeny and others. It describes quantum systems not just with a wave function evolving from the past to the future, but with two wave functions, one moving forward in time and one backward. According to this model, the present state of a particle is influenced by both its past and its future. What happens now is shaped by boundary conditions on both ends of the timeline, as if the particle is obeying instructions from two directions. This may sound metaphysical, but the math checks out, and it could explain the strangeness of quantum entanglement, where particles separated by vast distances appear to influence each other instantly, regardless of space or time. But what would retrocausality mean for you, a conscious observer moving forward through time? It suggests that your choices might not just shape the future, but refine the past, that memory isn't fixed, that the path that led you here is still, in some hidden way, fluid, waiting for completion. This connects to ideas in physics and even psychology. Some cognitive theories suggest that we perceive time with a delay, that the brain waits a fraction of a second to assemble events into a coherent story. This delay means your sense of now is always slightly in the past, reconstructed, not lived in real time. If the mind can reshape the past in memory, and quantum systems can be influenced by future measurements, then perhaps the boundary between before and after is thinner than we thought. Retrocausality also challenges the nature of free will. If future conditions can influence the present, are our decisions truly autonomous, or are they part of a greater symmetry, a feedback loop across time, where cause and effect dance together, inseparable? And then there's the philosophical weight. If retrocausality is real, then the future exists, in some form already. It's not a blank canvas, but a dimension, like space, that we move through. You can't affect what doesn't exist. So if the future can reach back, then the future is real, whether we've seen it or not. This is a radical departure from how we experience life. We think of the past as fixed, the present as fleeting, and the future as open. Retrocausality flips that. It suggests that the present is a meeting point, not just of what has been, but of what will be. Could we use this? Could retrocausality explain intuition, premonition, synchronicity? Some fringe thinkers suggest that what we call gut feelings or strange coincidences may be ripples from the future, echoes of events that haven't happened yet, but are already shaping our trajectory. Mainstream science doesn't go that far, but it does acknowledge that our understanding of time is incomplete. Einstein's relativity already showed us that time is relative. It stretches, compresses, and bends in the presence of mass and motion. Quantum physics suggests it may be even stranger, not linear, but entangled with observation and potential. So what do we do with this idea? Retrocausality doesn't let you send messages to the past. You can't warn your younger self. You can't undo a mistake, but it might mean that the future is not just a consequence, it's a participant. And if that's true, then perhaps every moment is not just shaped by memory, but by possibility. Not just where you've been, but where you're going. It means that your life is not a straight line, but a spiral, influenced by past choices and future states alike. It means that change doesn't just begin now. It might also echo backward, reshaping the meaning of everything that came before. And maybe, just maybe, this chapter of your life didn't start when you made a decision. Maybe it started when your future self reached back and whispered. Chapter 9. The Anthropic Principle. Is the universe tuned for you? Why is the universe so perfect for life? Not just any kind of life, but your kind. Carbon-based, DNA-driven, fragile and intelligent life that can wonder about its own existence. It's a question that has haunted physicists and philosophers for decades. The more we understand the laws of nature, the more one eerie truth emerges. The universe seems uncannily tailored for life to exist. This strange observation is at the heart of a deep idea known as the anthropic principle. And depending on how you interpret it, it either explains everything or nothing at all. Start with the basics. Our universe has physical constants, fixed numbers, like the gravitational constant, the strength of electromagnetism, the mass of the electron. These values don't change. They're not derived from other laws, they just are, but they matter deeply. If any of them were slightly different even by a fraction of a percent, atoms wouldn't form, stars wouldn't shine, chemistry wouldn't function, life as we know it would be impossible. Take the strong nuclear force, for example. It holds the nuclei of atoms together. If it were just 2% stronger, all hydrogen in the universe would fuse instantly in the early universe, leaving no fuel for stars. If it were 2% weaker, atomic nuclei would fly apart. No atoms, no matter, no light. Or consider the cosmological constant, the energy density of space itself. It controls the expansion rate of the universe. If it were even slightly larger, space would expand too quickly for galaxies to form. If it were smaller, the universe would collapse before stars could ignite. These are just two examples. There are dozens of finely tuned parameters, and all of them, every single one, land within the narrow range that permits complexity, stability, and life. So the question becomes why? Why do we live in a universe where life is possible, let alone one where it emerged, evolved, and began to ask these very questions? Enter the anthropic principle. At its simplest, the principle states the universe must have properties that allow life to exist, because otherwise we wouldn't be here to observe it. That sounds tautological, circular, even meaningless, but it has profound implications. There are two main versions of the anthropic principle. The weak anthropic principle says that we observe a life-permitting universe because only in such a universe could observers like us exist. The strong anthropic principle goes further, suggesting that the universe must have properties that allow for life, perhaps implying design, necessity, or purpose. In other words, is the universe fine-tuned for life by chance or by design? Or are there other universes with other constants where life never emerged, and we just happen to be in one of the rare hospitable ones? This leads to the concept of the multiverse. According to some theories, particularly those arising from string theory and eternal inflation, our universe might be just one of countless universes in a vast multiverse, each with different physical laws and constants. Most of these universes would be lifeless, dead, chaotic, but in a few, conditions would randomly allow for life. We, as observers, would naturally find ourselves in one of those rare islands of habitability, not because we're special, but because it's the only place we could possibly exist. This explanation is powerful. It removes the need for a cosmic designer. It makes life a statistical inevitability, not a miracle, but it also pushes the mystery one step further. If the multiverse exists, where is it? Can we test it, observe it, or is it forever beyond our reach? Some physicists argue that we'll never detect other universes, that they lie beyond the bounds of our observable cosmos. Others suggest that cosmic background radiation might hold subtle clues, like fingerprints of neighboring realities brushing against our own. Still, the anthropic principle remains controversial. Some scientists hate it. They argue that it explains nothing, that it's a philosophical trick used to cover up gaps in understanding. Others see it as an essential guidepost, a reminder that observation is not neutral, but embedded in context. After all, our very act of asking why is shaped by our own existence. We are not outside the system looking in, we are part of it. Our bodies, thoughts, and questions are built from the very laws we seek to explain. And that raises deeper questions. Is life a fluke, or a feature? Is consciousness an accident of chemistry, or a fundamental property of reality? Some thinkers speculate that life is not just permitted by the universe, but required, that the laws of physics are structured in a way that naturally leads to complexity, emergence, and eventually awareness. This idea borders on the metaphysical. It suggests that the universe wants to be known. That observation is not an afterthought, but the goal. But even without such grand ideas, the anthropic principle forces us to face the unlikely fact of our own existence. That we are here, that the constants are right, that the stars burn just long enough for planets to form, chemicals to combine, and questions to arise. And maybe that's enough. Maybe the mystery isn't meant to be solved, only seen. Maybe the fact that we can ask is the answer. Chapter 10. Emergent Spacetime. Is spacetime not fundamental? We take space and time for granted. They seem like the stage on which everything happens. The framework, the canvas. Without space, where would matter exist? Without time, how could anything unfold? But what if space and time aren't the foundation but the result? What if spacetime is not fundamental but emergent, like a mirage rising from something deeper, stranger, and entirely hidden from our senses? This is the startling idea explored in modern physics, that space-time itself may emerge from more fundamental building blocks, not particles or waves, but information, entanglement, and geometry. And if that's true, then reality as we experience it is not absolute, but constructed, assembled like a dream, piece by piece, from an invisible code. To understand where this comes from, we must return to the interface between quantum mechanics and general relativity, the two great pillars of physics. Quantum mechanics governs the small atoms, electrons, probabilities. General relativity governs the large planets, stars, and the curvature of space-time. Each works beautifully in its own domain, but when you try to put them together, to describe gravity at the quantum level, things break down. The math becomes incoherent. Infinity rears its head, something isn't fitting. And so physicists have been searching for a quantum theory of gravity, a model that unites both frameworks into a single description of reality. In that search, one radical possibility has emerged, that space-time is not a given. It's not part of the foundation. It emerges from quantum entanglement. Here's how the idea works. In quantum theory, particles can become entangled, their properties linked in such a way that the state of one instantly influences the other, no matter how far apart they are. Entanglement is not just a connection, it's a structure, a web of relationships that defines how information is shared. Now imagine this entanglement not as a side effect, but as the actual source of space. This is what physicists like Mark van Ramsdonk, Brian Swingle, and Juan Maldacena have proposed. That space arises from entanglement patterns in quantum systems. That distance, geometry, and even gravity are emergent properties, illusions that appear when many quantum states interact in just the right way. In other words, space is not empty. It's built, not from atoms, not from fields, but from information. One of the most powerful demonstrations of this comes from the AD-CFT correspondence, a discovery we touched on earlier. It links a quantum field theory on a flat surface to a gravity theory in a curved higher-dimensional space. It's as if the fabric of space and gravity unfolds from a purely informational system, like a 3D image encoded in 2D data. This correspondence is more than math. It suggests that space-time is not the arena, it's the product. And it might explain why gravity is so hard to quantize. If gravity and space are emergent, then trying to quantize them is like trying to find the molecules in a rainbow. You're missing the point. You're looking at the illusion, not the source. Some physicists even describe spacetime as a tensor network, a vast, entangled web of quantum nodes, where connection strength defines proximity, where geometry is not fixed, but woven from correlation. And if that's true, then reality itself is more like a computation than a construction, not a static thing, but a process, a flow of information. This also sheds new light on the nature of black holes. Black holes are puzzles. They bend space, distort time, and conceal information behind their event horizons. But in a holographic universe, the surface of the black hole, not the volume, contains all the information. This aligns with the Bekenstein-Hawking entropy formula, which shows that a black hole's entropy, a measure of its information, is proportional to its surface area, not its size. Once again, surface encodes volume, information encodes space. So what does this mean for you? It means that the space you occupy, your room, your body, the world, might not be out there at all. It might be a construct of correlations, a projection from deeper information, and time. Time might not tick independently. It might be a measure of how entanglement spreads, how change propagates in the underlying structure. In this picture, time and space don't exist on their own. They exist because of relationships. They are the shadows of a deeper, structureless reality. This isn't philosophy, it's serious physics, and it's gaining traction. Researchers at institutes like the Perimeter Institute, Stanford, and MIT are actively exploring models where entanglement builds geometry, where space-time is a derived quantity, not a gift, where the universe we see is not fundamental but emergent. This opens the door to entirely new ways of thinking about consciousness, matter, and existence. If space-time is not the foundation, then perhaps neither is matter. Perhaps the true foundation of reality is information, a vast, shimmering field of relations from which all things emerge. Some have called this the it-from-qubit paradigm, the idea that it, physical reality, emerges from qubits, the quantum bits of information. Reality in this view is not made of stuff, but of logic, code, pattern, correlation. And if this is true, then we are not objects in space. We are nodes in a network, embodied threads in a quantum web, woven not from matter but from meaning. It's a breathtaking idea, one that collapses the distinction between physics and philosophy, between the world out there and the thoughts in here. Because if space is built from information, then perhaps so are you. Chapter 11. The Mathematical Universe Hypothesis. Is reality made of math? You live in a world of things, of objects, trees, clouds, people, emotions. You feel, breathe, move. It all seems real, solid, sensory, intuitive. But what if, underneath all of it, there is no substance, only structure? What if the universe is not made of particles, waves, or even energy, but of mathematics? This isn't a metaphor. It's not poetic, it's a radical scientific theory that reality is not just described by math, it is math. This idea, known as the mathematical universe hypothesis, was proposed most famously by physicist Max Tegmark, and if he's right, then everything, from the smallest particle to the largest galaxy, from your brain to your dreams, is a mathematical structure. Let's step back. Physics has always used mathematics to describe the world. Newton described motion with equations. Einstein wrote the geometry of space-time in tensor form. Quantum mechanics lives in the abstract world of wave functions and operators. Wherever we look, math is not just a tool, it's the very language of reality. So Tegmark asks a simple question: why is that? Why should a human-invented system, math, match the behavior of the physical world so perfectly? Why do equations designed on a chalkboard in isolation end up describing the behavior of black holes, atoms and galaxies? Maybe it's not a coincidence. Maybe it's because the physical world is mathematics, not just governed by math, not just built on math, but literally identical to a mathematical structure. In this view, every particle is a point in a vast geometric object, every field is a function, every event is a computation. Your mind, your thoughts and memories are patterns of information unfolding along mathematical pathways. Now take that a step further. If the universe is a mathematical object, then it's just one of many. Mathematics is full of consistent structures, number systems, topologies, algebras, symmetries. If each of these corresponds to a potential universe, then reality is not a single world, but an ensemble, a mathematical multiverse. We exist in the one that supports conscious observers, the structure that happens to unfold in a way that allows minds to arise. Tegmark calls this the level 4 multiverse, the highest and most abstract form of reality. In it, every consistent mathematical structure exists physically. If it's logically possible, it is real somewhere. That's hard to grasp, but let's try. In our universe, the laws of physics are built on certain symmetries and constants. We think of those as facts of nature, but in the mathematical universe view, they are simply features of our particular structure, like the properties of a specific geometric object. Other structures may have different laws, different constants, different logic. In some, space may have more than 3 dimensions. In others, time may not even exist. But each of those structures is just as real as ours, just expressed in a different mathematical language. This leads to a mind-bending conclusion. The ultimate reality is not physical at all, it's mathematical. The world you see is an expression, a projection of an abstract structure. You are not matter experiencing math, you are math experiencing itself. That might sound cold, lifeless, but mathematics is not dry symbols on paper. It is the study of patterns, relationships, transformations, the architecture of possibility. Within it lies all beauty, all logic, all emergence. And if consciousness can arise from pattern, then math contains not just thought, but feeling. Critics of the mathematical universe hypothesis argue that it's untestable, that it pushes science into metaphysics, that it tells us more about human cognition than about reality. But Tegmark responds, what if we've been making a category error? What if the universe is not a machine but a theorem? After all, our best theories, general relativity, quantum field theory, the Standard Model, are mathematical frameworks. They don't just describe reality, they are reality. At the deepest level, particles are excitations in fields. Fields are governed by symmetries, and symmetries are mathematical objects. So why draw a line between math and matter? One implication of this view is that consciousness, the sense of self, is not tied to a particular substrate. If the mind is a pattern, then any system that instantiates that pattern is conscious. In principle, it doesn't matter whether the substrate is neurons, circuits, or equations. The pattern is what matters. This idea resonates with other theories we've explored: the holographic mind, the simulation hypothesis, quantum immortality. All of them suggest that what we experience as reality is not ultimate, but emergent. That behind the curtain of perception lies something abstract, eternal, and precise. But perhaps the most powerful consequence of the mathematical universe hypothesis is its simplicity. It offers a single framework that can include every consistent reality, every physical law, every possible configuration. In a way, it's the ultimate theory of everything, not just this universe but all possible universes. So what does that mean for you? It means that your existence is not random. You are the expression of a structure, a solution to a vast, complex equation. Your thoughts are not separate from the universe. They are the universe reflecting on itself. It also means that you may never find a final answer, because in a mathematical universe, questions are not flaws, they are features. Each leads to deeper structure, more nuance, more exploration. The more we know, the more there is to know. And maybe that's the point. Maybe existence is not about reaching the end of a story, but about being part of the story. A theorem unfolding in real time, a pattern that sees itself, knows itself, and asks, what am I? You are not outside the equation, you are the equation. And the more you understand it, the more you come alive. Chapter 12. The Shadow of Infinity. Can the universe be truly infinite? What if the universe has no edge, no boundary, no end? When you look up at the night sky, you see distance, depth, vastness. But eventually it must stop, right? There has to be a final star, a farthest galaxy, a last particle at the edge of it all. Or does there? The concept of infinity is one of the most mysterious in all of science. It's simple to imagine, but nearly impossible to comprehend. A quantity without limit, a horizon that never arrives, a forever that never ends. And when it comes to the universe, the question is haunting: is reality infinite, or just very, very big? Let's begin with the shape of space. Cosmologists describe the geometry of the universe using Einstein's equations of general relativity. The universe can be flat, closed, or open, corresponding to different possible shapes. A flat universe is infinite and uncurved, like an endless sheet. A closed universe curves back on itself, like the surface of a sphere, but in higher dimensions. An open universe expands forever, like a saddle or a hyperbolic plane. Current data, especially from measurements of the cosmic microwave background, suggests the universe is very, very close to flat. So close, in fact, that if it is curved at all, the curvature is so small we can't detect it. That suggests one possibility: the universe is infinite in extent. But what does that actually mean? If the universe is infinite, then space goes on forever. There is no edge, no outside, no limit. No matter how far you travel, there is always more galaxies, more stars, more emptiness. You could go on for 1 trillion lifetimes and never reach a wall. It also means that matter could be infinite, that every possible configuration of particles occurs, not once, but countless times. That includes you. In an infinite universe, there may be copies of you, scattered across the cosmos, not metaphorical twins, but literal arrangements of atoms identical to your body, your brain, your memories, living parallel lives in distant regions of space. These duplicates aren't science fiction. They are the logical consequence of infinite space with finite configuration. There are only so many ways atoms can arrange themselves into a human. In an infinite space, all arrangements occur and recur again and again. That's hard to accept, but math insists. If the universe is infinite and statistically uniform, then your life is not unique, only localized. Your existence is part of a cosmic mosaic that includes all possibilities. Some find that disturbing, others find it beautiful, but it doesn't stop there. Infinity also raises questions about energy. If space is infinite, is the total energy of the universe also infinite, or does it somehow cancel out, with positive energy from matter balanced by negative energy from gravity? This is an active area of research. Some theories suggest that the net energy of the universe is zero, that the universe came from nothing, but that nothing includes opposing forces that perfectly cancel. Others say energy conservation doesn't apply on cosmic scales the way it does locally. And what about time? If space is infinite, is time infinite too? Will the universe last forever? As we saw in Chapter 6, current models predict a slow fade, a heat death of increasing entropy and decreasing structure. But if time never ends, that process never finishes. Reality becomes an eternal drift into silence, infinite time, without change. But maybe infinity is an illusion. Some scientists argue that true infinities don't exist in nature, that they are artifacts of incomplete theories. Infinity appears in our equations. Perhaps it's a sign the math has broken down. After all, infinities are notoriously problematic in physics. They pop up in black holes, singularities, quantum field divergences, and early universe models, and they often signal a need for better theory. Perhaps the universe only seems infinite because it's vast beyond measure. Maybe it loops back on itself, like a higher dimensional sphere. If you traveled far enough in a straight line, you might return to where you started, not by hitting a wall, but by curving through space itself. Others argue that space is quantized, that it comes in discrete units, like pixels on a screen. If that's true, then there is a finite amount of space, even if it feels smooth and continuous. And yet, we keep seeing infinity. In math, it's everywhere. In geometry, calculus, set theory. In physics, we model the universe with infinite precision. And some physicists believe that infinity is not a bug, but a feature, a window into the deepest truths of reality. Infinity also forces us to confront our limitations, because if the universe is infinite, then we can never know it all. We are finite creatures, finite brains, finite time, finite scope. We see a sliver, we touch a breath. The rest lies beyond, unreachable, unknowable. And yet, we reach anyway. We build telescopes to see farther, equations to describe more, stories to make sense of what cannot be touched. And in doing so, we mirror the infinity we seek, not in scope, but in curiosity. Because the real power of infinity is not in its size, but in what it reveals. It shows us that some truths are not about ends, but about unfolding, not about final answers, but about eternal questions. So is the universe infinite? We don't know, but the fact that we can ask, the fact that we can imagine it, may be the most infinite thing of all. Chapter 13. The Cosmic Censorship Hypothesis. Are singularities always hidden? At the heart of a black hole, something terrifying lies buried. Not a monster, not a tunnel, but a breakdown of the universe itself. A singularity, a place where gravity becomes infinite. Space folds into a point, and the known laws of physics cease to work. Singularities are not just weird, they are incomprehensible. They mark the limits of our understanding, the places where equations fail and time may come undone. And yet, they're real. Predicted by Einstein's equations, confirmed by general relativity, hiding in the darkness of every black hole. But here's the strangest part. We never see them. They're always hidden behind a veil, a boundary we call the event horizon. It's a one-way door. Once something crosses it, no light, no signal, no escape is possible. From the outside, we can't peer in. The singularity remains forever concealed. This observation led physicist Roger Penrose to propose a provocative idea, the cosmic censorship hypothesis. It's a kind of universal modesty clause, a law of nature that says singularities must always be hidden. No naked singularities, no exposed tears in the fabric of space-time. The universe, he suggests, censors its own breakdowns. But why? Because naked singularities would shatter predictability. They would allow infinite gravity, undefined curvature, and perhaps even time loops to be visible, accessible, from the rest of the universe. That would ruin the very thing that makes physics work, determinism, the ability to predict the future from the present. When singularities are safely locked behind horizons, we can ignore their madness. We can study what happens outside and pretend the breakdown doesn't matter. But if one were to appear in the open exposed, all bets would be off. Reality itself could become unstable, unpredictable, even paradoxical. So Penrose proposed that nature forbids this, that any situation which might expose a singularity is prevented, either by collapsing into a black hole, or never forming in the first place. This is the cosmic censorship conjecture, and for decades it has guided the way physicists think about black holes, singularities, and the structure of the universe. But is it true? Mathematically, we don't know. The conjecture is still unproven, and in certain solutions to Einstein's equations, naked singularities can form, under just the right conditions, in just the right configurations. These are rare, exotic, but not impossible. One example is the Kerr solution, which describes a rotating black hole. If it spins fast enough, near its maximum limit, it might fail to form an event horizon. The singularity would then be exposed, naked, visible. In theory, that could allow us to peer into the heart of a singularity, to see not just matter crushed to a point, but the breakdown of space and time, a place where causality dissolves and time might even reverse. And that is deeply dangerous. Naked singularities might allow closed time-like curves, paths through space-time, that loop back themselves, in other words, time travel, the kind that violates causality and opens paradoxes. What happens if you send information into such a loop? What happens if you receive a signal from your future self? What happens if the laws of physics allow themselves to break? These are the nightmares of theoretical physics, and they are why cosmic censorship is so important. It's not just a guess, it's a safeguard, a firewall between the parts of the universe we can understand and those we can't. But maybe the universe isn't so modest after all. In recent years, physicists have begun to explore violations of cosmic censorship under extreme conditions like scalar fields, high angular momentum, or specific initial states. Simulations suggest that naked singularities can form. These scenarios remain highly idealized, but they suggest that the cosmos might occasionally lift its veil. And if it does, what might we see? We don't know. That's the point. A singularity is undefined. Infinite curvature, zero volume, no coordinates. It's not a place. It's the failure of place. The point where space-time becomes meaningless. And yet it's part of our best theories. It lies at the heart of black holes, and perhaps at the origin of the universe itself. Yes, the Big Bang may also have been a singularity, a moment when time began, when all space collapsed to a point, or perhaps, more accurately, the first moment when our description of time began. What came before? Nothing, something. The truth is, we don't know, because singularities don't just lie in time. They may lie outside it. Some physicists hope that a quantum theory of gravity, like string theory or loop quantum gravity, will resolve singularities, that instead of infinities we'll find new structure, foam, loops, strings, discrete spacetime, something tangible, something real. But until that theory arrives, we live in the shadow of singularities, blind to what lies inside. And so we rely on cosmic censorship to keep the peace, to maintain order, to hide the places where our equations collapse. But maybe, just maybe, the universe lets the curtain slip. Maybe somewhere out there, a naked singularity exists. Maybe it's not a monster, but a window, a glimpse into the next layer of truth. And maybe we'll see it. One day. Chapter 14. Non-locality. Is the universe instantly connected? When you move your hand, the effect is local. Muscles contract, nerves fire. The sensation is confined to a point in space and time. Action happens here, result happens here. That's locality. It's how we expect the world to work. But in the strange world of quantum mechanics, that expectation breaks down. There are experiments proven and repeated that show something profound. What happens in one place can instantly affect what happens somewhere else, even if the two places are separated by light years. This is not speculation. It's a fact. It's called quantum non-locality, and it changes everything. To understand it, we need to talk about entanglement. Imagine two particles, say electrons, that interact in such a way that their properties become linked. One spins up, the other spins down. The exact values aren't known, only the relationship. Together, they form an entangled pair. Now take one of those electrons and fly it to the other side of the galaxy. Keep the other one in your lab. Measure the spin of the lab electron, and instantly, the spin of the distant one is determined. No signal travels between them. No force bridges the gap, and yet, the result is correlated, always, perfect. This was the nightmare of Albert Einstein, who famously called it spooky action at a distance. He didn't like it. He thought there had to be some hidden variable, some local explanation we weren't seeing. But in the 1960s, physicist John Bell devised a test. He showed that if local hidden variables were responsible, certain mathematical limits, now called Bell's inequalities, should never be violated. And then, experiments violated them, repeatedly, decisively, most famously by Alain Aspect in the 1980s, and confirmed again and again in modern labs with ever greater precision. The conclusion? Local realism is dead. Either the universe is non-local, or reality doesn't exist in a definite state until observed, or both. That means we live in a world where space is not a barrier, where particles remain connected, regardless of distance, where the very idea of separation might be an illusion. But what does non-local really mean? It doesn't mean you can send messages faster than light. That would violate relativity. Entanglement correlations can't be used for communication, but they do show that information, or at least correlation, is not confined by space. It's as if the universe knows how things are connected, even when those connections are physically impossible in classical terms. Some physicists believe this points to a deeper truth, that space itself is not fundamental, that what we call distance is not a fixed background, but a pattern emerging from quantum relationships. Remember Chapter 10, Emergent Spacetime. Non-locality may be a hint of that deeper layer, where space is just the shadow of entanglement. If space is an illusion, then non-locality is not magic. It's just business as usual in a universe where everything is connected underneath. Some go further. They suggest that consciousness itself may be non-local, not confined to the brain, but participating in a field that spans the cosmos. It's speculative, but the idea that the mind is not separate but embedded finds echoes in both quantum theory and ancient philosophy. Others explore how non-locality might lead to new technologies, quantum computers that use entanglement to solve problems classical machines never could, quantum encryption that's theoretically unbreakable, quantum networks that allow instant, secure coordination, not with signals, but with shared states. And then, of course, there's the metaphysical question. If everything is entangled, if distance is not fundamental, then are we truly separate beings? Or are we threads in a single fabric, points in a web that stretches across time and space, linked not by proximity but by pattern? Non-locality suggests a universe without edges, not just spatially, but conceptually. A reality where every part reflects the whole, where the laws of physics don't play out like dominoes, but like music. Harmony spread across distance, notes resonating in synchrony. This vision is not easy. It's not intuitive, but it might be real, and if it is, then everything we thought was separate is part of something deeper. You and I, stars and atoms, cause and effect, all connected, all one. Chapter 15, The Planck Scale. Where reality breaks down. At some point, the universe stops making sense. Not because it disappears, but because the very tools we use to understand it, space, time, energy, causality, begin to dissolve, and the place where that happens is not out in the distant cosmos or hidden behind black holes. It is far smaller, so small in fact, that we can't even see it. This mysterious realm is known as the Planck scale, the point at which our understanding of physics breaks down completely. To even begin to grasp the Planck scale, we must understand that it is not a single place or thing, but a set of extreme limits. The Planck length, the Planck time and the Planck energy represent the smallest meaningful measurements of space, time, and energy in our universe. The Planck length is unimaginably tiny, about 1.6 times 10 to the negative 35 meters. For context, that's smaller than a proton by a factor of roughly 100 billion. It's a distance so short that it becomes meaningless to think of space as smooth. If you tried to zoom in to observe it, the very act of measuring would create so much energy that you'd form a black hole, instantly erasing what you were trying to study. The Planck time is equally bizarre. It is the smallest possible unit of time that makes physical sense, approximately 5.4 times 10 to the negative 44 seconds. Below that scale, we have no idea what time even means. Does it tick? Does it flow? Does it shatter into something else entirely? Our equations don't, they simply stop being useful. Physics becomes silent. And then there's the Planck energy, an inconceivably large amount of energy, roughly equal to 10 to the 19th giga-electron-volts. This is the amount of energy it would take to probe distances as small as the Planck length. It's more energy than is currently producible in any experiment, more than all the particle accelerators on Earth could ever generate, even combined. At the Planck energy, gravitational and quantum forces are believed to be equal in strength. That's critical, because it's at this scale that the two major frameworks of physics, general relativity and quantum mechanics, are both simultaneously required, and yet they contradict each other. General relativity describes gravity as the curvature of spacetime. It tells us how planets orbit stars, how black holes form, and how the universe expands. It's smooth, continuous, and deterministic. Quantum mechanics, on the other hand, governs the behavior of atoms and subatomic particles. It's probabilistic, discrete, and deeply non-intuitive. Both theories are stunningly successful, but when you try to apply them together, as you must at the Planck scale, they collide. They don't fit. Their math becomes incompatible. Predictions become infinite. Logic collapses. That's why the Planck scale is not just small, it is the boundary of human knowledge. It is the edge of what we can currently describe about the universe, and what lies beyond it remains one of the greatest mysteries in all of science. One of the most intriguing possibilities is that space itself may not be continuous. We tend to imagine space as a smooth fabric, a background grid on which all physical processes unfold, but at the Planck scale, that fabric may unravel. Instead of a seamless field, space may be quantized, made up of tiny, indivisible units, like pixels on a screen, or grains of sand in a desert. This is the idea behind theories like loop quantum gravity, which proposes that space is composed of loops of quantum fields. According to this model, Areas and volumes come in discrete chunks. You cannot have half a Planck volume, just as you cannot have half a particle of light. Another possibility comes from string theory. Instead of imagining particles as point-like dots, string theory proposes that they are tiny vibrating strings of energy. The type of vibration determines the properties of the particle, its mass, charge, spin, and behavior. These strings are believed to be on the order of the Planck length. But here's where it gets even stranger. In string theory, extra dimensions of space may exist. Dimensions that are curled up so tightly that we don't experience them directly. They could be hiding in the Planck scale structure of reality, shaping the universe from behind the scenes. But string theory is not the only attempt to explore this realm. There are other approaches, some known, others still forming in the minds of theorists. What they all share is the understanding that something has to change. Our classical ideas about geometry, continuity, and causality cannot survive the trip to the Planck scale. And that trip is not just a thought experiment. There are real-world places where conditions reach Planck-level extremes, and we don't yet know what happens there. The center of a black hole is one example. According to general relativity, everything that falls into a black hole collapses to a singularity, an infinitely dense point. But infinities are usually a red flag in physics. They indicate that something is wrong with our model, that our tools are no longer valid. At the singularity, space-time curvature becomes infinite, density becomes infinite, and we have no working theory of what takes place there. The same issue arises at the moment of the Big Bang. If we rewind the universe all the way back in time, it contracts to a point of infinite density and temperature. Again, a singularity. Again, the equations fail, but something happened. The universe began, time started, space inflated, matter emerged, and whatever process made that possible happened at or below the Planck scale. Physicists believe that, if we could understand reality at that level, we might answer some of the deepest questions in science. Why did the universe begin in such a low entropy state? Why are the fundamental constants of nature so finely tuned? What is dark matter? What is dark energy? Could the entire universe be a hologram, projected from quantum information on its boundary? These are not idle curiosities, they are clues, and the Planck scale is where the answers may hide. Even time itself may be an emergent phenomenon. Some theories suggest that time is not a fundamental property of the universe, but a byproduct of change. If so, then below the Planck scale, where no measurable change can occur, time may cease to exist in any meaningful way. Without time, there is no before or after. Only states, relations, entanglements. The arrow of time may not break. It may simply not apply. There's a profound philosophical implication here. When we imagine the universe, we picture things. Particles, waves, forces, but at the Planck scale, there may be no things at all. Just information, just logic, just patterns of relation. Some physicists now suggest that what we call physical reality is actually built from information. This is sometimes described as it from bit, the idea that what we perceive as matter and energy is fundamentally the result of informational states. If that's true, then the Planck scale is not just the end of physics, it's the beginning of something new. A different language, a different ontology, one in which space, time, matter, and energy are not primary but secondary, emergent from a deeper informational substrate. And yet, for now, we remain locked out. Our most powerful particle accelerators cannot probe the Planck scale. The energy required is simply too great. We can simulate aspects of it in computer models. We can study the math, but we cannot touch it. Not yet. Maybe not ever. It may always lie just beyond our reach. A cosmic boundary we can only approach through thought. But that doesn't stop us. In fact, it's what drives us. The Planck scale is not just an end. It's a challenge, a frontier, the place where the known ends and the possible begins. It is the edge of reality as we understand it, and the doorway to whatever comes next. So the next time you look up at the night sky, remember, the universe is not only vast, it is deep, and somewhere, far smaller than the smallest thing you can imagine, lies the truth about what everything is, what everything was, and what everything might still become. Chapter 16, Symmetry Breaking. How the Universe Chose Its Shape. Imagine the earliest moment of the universe. Not a moment after the bang, not after atoms or galaxies, but the very beginning, when the cosmos was so hot, so dense, so unified, that everything was the same. No stars, no elements, no directions. Just pure energy, balanced in perfect symmetry. Every point of space identical, every force indistinguishable. It was a time when nature had not yet made any decisions. Everything was equal. But it didn't stay that way. At some point, that perfect symmetry cracked. It didn't explode or vanish. It broke. And when it broke, the universe began to take shape. Forces separated, particles differentiated, directions gained meaning. The symmetry was lost. And from that loss, the structure of everything we know was born. This process, known as symmetry breaking, lies at the heart of how the universe became what it is. It may sound abstract, but it explains why there are atoms, stars, and even time itself. Symmetry breaking is one of the most powerful concepts in modern physics. In simple terms, symmetry is when a system remains the same, even after being transformed. A perfect sphere looks the same from any angle. That's rotational symmetry. A snowflake has six-fold symmetry. Rotate it 60 degrees, and it looks unchanged. In the early universe, the laws of physics were believed to have a much higher degree of symmetry than they do now, but this symmetry wasn't permanent. It was unstable. Think of a pencil balanced perfectly on its point. In theory, it could stay upright forever. The laws of physics don't prefer any direction for it to fall, but the real world isn't perfectly stable. Sooner or later, some tiny fluctuation, a vibration, a breeze, causes the pencil to fall in one direction. That direction isn't special. It's random, but once the pencil falls, a symmetry has been broken. Before, all directions were equal. After, one is chosen. The system has gone from symmetric to asymmetric, not because the laws changed, but because the state of the system selected a specific outcome. That's the essence of spontaneous symmetry breaking. The rules stay the same, but the result chooses a path. And in the early universe, this happened on a cosmic scale. At first, all the fundamental forces, gravity, electromagnetism, the strong and weak nuclear forces, were thought to be unified. They were different expressions of a single force, but as the universe expanded and cooled, this unity fractured, the symmetry broke, and the forces separated, each acquiring distinct characteristics. This wasn't just a cosmetic change, it shaped the very possibility of matter. One of the most important examples of symmetry breaking in modern physics is the Higgs mechanism. In the standard model of particle physics, particles acquire mass, not because they are inherently massive, but because they interact with a field, the Higgs field, that permeates all of space. When the universe was still extremely hot, the Higgs field had zero value everywhere. It was symmetric. But as the universe cooled, the field settled into a new lower energy state that wasn't symmetric. This spontaneous change broke the symmetry, and in doing so gave mass to particles. Without that breaking, matter as we know it could not exist. The Higgs field is like a crowd of people in a room. When no one's paying attention, you can walk through the room freely. But if someone famous enters, the crowd clusters around them. Moving through the room becomes harder. The person now feels resistance. They act like they have more mass. In a similar way, particles interacting with the Higgs field gain mass, based on how strongly they interact. Some particles, like photons, don't interact with it at all. They remain massless. Others, like electrons and quarks, do, and gain mass accordingly. This breaking of symmetry didn't happen once, it happened multiple times. As the universe cooled in stages, different symmetries broke at different scales. Each stage gave rise to new structures, new forces, and new rules. It's like a series of phase transitions from steam to water to ice, each with distinct behaviors, all governed by the same underlying physics. But symmetry breaking doesn't just explain particles, it also explains patterns we see in nature, why snowflakes form with specific structures, why galaxies rotate in spirals, why some molecules twist left or right. In every case, the system had many possible configurations, but it selected one, breaking the symmetry, creating order and locking in structure. And it might go even deeper. Some cosmologists believe that the very fabric of space-time itself may have emerged from symmetry breaking. In the earlier state before time flowed and space expanded, the universe may have existed in a purely symmetric quantum state. No directions, no dimensions, no boundaries. Then something changed. The symmetry broke. A particular direction of time was chosen. Space unfolded, entropy gained meaning. The universe began. This would mean that even time is not fundamental, that it emerged as a result of the universe choosing a direction. Not because that direction was special, but because some fluctuation pushed it one way instead of another. Time, then, is the residue of broken symmetry, a relic of randomness set into motion. But what causes the symmetry to break in the first place? Is it pure chance? Is it driven by quantum fluctuations? Are there deeper laws at play, laws we haven't yet discovered? No one knows. But the idea that our entire universe is the product of a broken symmetry gives rise to an even stranger possibility, that there could be other universes where the symmetry broke differently. In those universes, the laws of physics might be completely different. Forces might not have split in the same way. Particles might behave differently. Chemistry might be impossible. Time might flow backward. These universes would be inaccessible to us, but they could exist. Parallel outcomes of the same initial conditions, diverging based on how their symmetries fractured. In that sense, symmetry breaking is not just a scientific idea, it is a philosophical one. It suggests that the universe in its most primal form contained all possibilities, and that what we observe is one expression among many. It suggests that our universe is not the only way reality could look, but simply the result of a cosmic coin toss, frozen in place. And that raises another deep question. If the universe began in a state of perfect symmetry, complete balance, zero information, total uniformity, then how did complexity arise? How did structure, order, and meaning emerge? The answer lies not in the symmetry itself, but in its breaking. When symmetry is broken, new degrees of freedom appear. The system gains richness, new behaviors become possible, new laws arise. It's a paradox of sorts. By becoming less perfect, the universe became more interesting. By giving up symmetry, it gained structure. In breaking, it began to build. This principle echoes across disciplines, from physics to biology, from art to philosophy. In every system, order often emerges, not from rigid structure, but from the instability of symmetry. Crystals form when atomic symmetries break. Life evolves when genetic balance is disrupted. Music gains emotion when patterns are bent, not followed perfectly. Even our own consciousness may arise from the brain's ability to balance order and chaos, symmetry and asymmetry in its firing patterns. So when you look at the universe, its stars, its laws, its breath, remember this. Everything you see exists not because the universe was perfect, but because it allowed itself to break, and in that breaking it found form, in that fracture it found beauty. Chapter 17: Vacuum Energy. Why empty space isn't empty. When you think of a vacuum, you probably imagine emptiness, a pure, featureless void, no particles, no light, no sound, just a cold, eternal silence. In classical physics this was the definition of nothing, the absence of everything. But in modern physics the vacuum is not nothing at all. In fact, it may be the most active, energetic, and mysterious thing in the entire universe. This strange idea is called vacuum energy, and it completely redefines what it means for space to be empty. According to quantum field theory, the foundation of modern particle physics, even in the total absence of matter, fields still exist. Fields like the electromagnetic field, the Higgs field, and many others, are always present, even in what we call a vacuum. These fields are never completely still. They fluctuate, jittering with quantum uncertainty, and those fluctuations give rise to energy, vacuum energy, that permeates all of space. At first glance, this seems contradictory. How can nothing have energy? How can emptiness have structure? But this is exactly what quantum theory predicts. In fact, the uncertainty principle, which states that you can't know both the position and momentum of a particle exactly at the same time, implies that even empty space cannot be perfectly still. If it were, we'd know both values precisely. The field would be at rest, and we'd know it. But quantum mechanics forbids that. Instead, even when nothing is there is still something happening. Fluctuations, virtual particles, tremors in the fabric of reality. These fluctuations can't be directly observed, but their effects are real. One of the most famous demonstrations is the Casimir effect. If you place two uncharged parallel metal plates very close together in a vacuum, they will attract each other, not because of any external force, but because of vacuum energy. The plates restrict the kinds of virtual particles that can appear between them, altering the energy density of the vacuum. The result is a measurable force. This shows that the vacuum has structure, pressure, and behavior. It's not just empty space, it's a quantum engine. But vacuum energy is more than just a curious lab experiment. It plays a role in the largest structures in the universe. In cosmology, the concept of vacuum energy is tied to dark energy, the mysterious force that's causing the universe's expansion to accelerate. When we measure the way galaxies move and the way the universe is growing, we find that some unseen energy is pushing space apart. This energy doesn't clump like matter. It doesn't dilute as space expands. It seems to remain constant, or nearly so, across all of time and space. One possible explanation is that this dark energy is vacuum energy, the baseline energy of empty space. If that's true, then the vacuum is not just seething with fluctuations on the smallest scales, it's also stretching the cosmos on the largest ones. The same nothingness that vibrates at the Planck scale could be pushing galaxies apart billions of light years away. But this leads to a problem, one of the biggest unsolved puzzles in physics. When we calculate the vacuum energy predicted by quantum field theory, the result is enormous. Truly colossal. One estimate suggests that the vacuum should have about 10 to the power of 120 times more energy than we observe. That's a 1 followed by 120 zeros, far more than all the matter, radiation and forces in the universe combined. But we don't see that energy. The universe isn't being torn apart. Galaxies still form. Stars still shine. Somehow, the enormous energy of the quantum vacuum is either hidden, cancelled, or misunderstood. This discrepancy is called the cosmological constant problem, and it's considered one of the greatest mysteries in theoretical physics. Why is the vacuum energy so much smaller than it should be? Is it exactly zero but not quite? Is there some symmetry or mechanism that cancels it out? Or is our understanding of quantum fields and gravity fundamentally flawed? No one knows for sure. It's an open question that cuts to the heart of our models of reality. Still, we cannot deny that vacuum energy exists. We can measure its effects. And some theories even suggest that it might not be constant, that the vacuum may evolve over time. In these models, sometimes called quintessence, the vacuum energy is not a fixed property, but a dynamic field that changes as the universe expands. If true, this could help explain why dark energy became dominant only recently in cosmic history, and why the expansion rate is increasing now, not earlier or later. Vacuum energy also raises the possibility of vacuum decay, a frightening if extremely speculative scenario. In quantum field theory, the vacuum we live in might not be the lowest possible energy state. It might be a false vacuum, a local minimum that appears stable, but isn't the absolute bottom of the energy landscape. If that's true, then a quantum fluctuation could cause the vacuum to tunnel into a lower state, releasing enormous energy and rewriting the laws of physics in the process. If such a transition occurred, it would happen at the speed of light. A bubble of true vacuum would expand outward at nearly the speed of causality, and everything inside would be obliterated. Matter would disintegrate. Chemistry would stop. Even space and time might become unrecognizable. This is not a fantasy. It is a real possibility predicted by some models of quantum fields and cosmology. Fortunately, current evidence suggests that our vacuum is stable, or at least metastable on timescales far longer than the age of the universe. But the fact that such an event is even possible shows just how strange and delicate our reality really is. Yet vacuum energy is not all destruction and fear, it may also be the source of reality itself. Some cosmologists believe that the universe began as a fluctuation of vacuum energy, that the Big Bang was not the explosion of matter into space, but the emergence of space, time, and matter from a quantum fluctuation in a high-energy vacuum. In this view, the universe is not a one-time event, but a statistical inevitability, a ripple in the quantum sea, one of many that might arise and fade over infinite time. This idea connects with the theory of inflation, a period of extremely rapid expansion in the early universe, driven by a kind of vacuum energy. According to inflation theory, the universe grew from subatomic size to macroscopic scale in a fraction of a second, smoothing out irregularities and setting the stage for everything that followed. Inflation explains the large-scale uniformity of the cosmos, the tiny variations that led to galaxy formation, and perhaps even the multiverse itself. In some versions of inflation, the vacuum never completely decays. Instead, it keeps producing new regions of space, each with its own laws and constants, a process called eternal inflation. In this scenario, our universe is just one bubble in a vast cosmic foam, each bubble with its own vacuum energy, its own physics, and its own story. And all of this, all of it, begins with the vacuum. What once seemed like nothing turns out to be everything, a place with no particles, no mass, no direction, yet full of potential, full of power, full of secrets. So the next time you stare at empty space, think again. It is not silent. It is not dead. It is alive with fields and fluctuations. It births particles and bends light. It expands the universe and holds the keys to its origin and fate. The vacuum is not the absence of reality. It is the foundation of a restless ocean beneath the calm surface of existence. And maybe, just maybe, the most profound truths are not found in things but in the spaces between them. Chapter 18: Dimensional Expansion. Did the universe grow more dimensions than we see? We live in a world of 3 dimensions: length, width, height. Add time, and we arrive at the 4-dimensional framework of space-time described by Einstein. This is the world we move through, the world we touch and observe. But what if this visible world is only a slice, a low-dimensional shadow of a much richer reality? What if the universe has more dimensions than we can perceive, and those extra dimensions are still shaping heaven from gravity to the birth of galaxies? The idea that reality might contain more than 3 spatial dimensions is not just science fiction, it's a serious proposition in modern physics. Theories like string theory, and its more generalized cousin, M-theory, require more dimensions to work, not just 1 or 2 extra but as many as 10 or 11 in total. These dimensions aren't simply stacked on top of the ones we know, they are tightly curled, hidden, and possibly vibrating in ways that influence the universe at every scale. In our everyday experience, we don't see these dimensions. We navigate forward and backward, side to side, up and down, but no more. Still, there's nothing in the laws of mathematics that limits space to 3. A point can exist in any number of dimensions. The challenge is observing the effects of those hidden axes. Why don't we see or move through them? Why are we confined to this 3-dimensional prison? One explanation is that higher dimensions are compactified, curled up into loops so small that we can't detect them. Imagine a tightrope. To an ant walking along the rope, it's a large, one-dimensional path forward and backward. But to a microscopic mite, the rope has a hidden 2nd dimension. It wraps around, that circular path is invisible from afar, but it's, similarly, extra dimensions in our universe might be folded in on themselves at scales near the Planck length, undetectable with current instruments but still real and influential. If this is true, then those extra dimensions may explain some of the deepest puzzles in physics. For example, why is gravity so weak compared to the other fundamental forces? It governs the motion of planets and stars. Yet it's billions of times weaker than electromagnetism. One hypothesis is that gravity isn't truly weak, it's just leaking into extra dimensions. While electromagnetic and nuclear forces are confined to our familiar 3-dimensional world, gravity might spread out through additional dimensions, diluting its apparent strength in our observable space. Some models even suggest that our entire universe might be a brane, a 3-dimensional surface floating in a higher dimensional space, like a soap film drifting through air. In these brain world scenarios, we are stuck to this surface, unable to move into the higher dimensions, but gravity and other forces might not be. The bulk, the higher dimensional volume beyond our brain, could contain other brains, other universes, or even other versions of ourselves. If this sounds strange, it's because it is. We have no direct evidence of these higher dimensions, but they remain mathematically consistent and theoretically compelling. In fact, they might be necessary to unify all forces under a single framework. Superstring theory, for instance, requires exactly 10 dimensions for the equations to hold together without contradiction. MEM theory, a broader structure, suggests 11. These dimensions allow the equations to balance. They give particles their properties. They help eliminate infinities that would otherwise wreck the theory. But where did these extra dimensions come from? Were they always there, or did they emerge as the universe expanded? This brings us to the idea of dimensional expansion, the notion that the number of large extended dimensions in the universe may have evolved. In the earliest moments after the Big Bang, the universe may have had more dimensions than we see today, but for reasons we don't yet understand, only 3 of them grew large. The others remained compactified, curled into loops too small to detect. Why 3? Why not 4, or 5, or 10? No one knows for sure. But one possible answer lies in stability. Simulations show that when more than 3 dimensions expand, the resulting universe becomes dynamically unstable. Gravity fails to coalesce matter, atoms can't form. Complexity falls apart. In 3 dimensions, though, orbits are stable. Fields behave well. Stars ignite. Life perhaps becomes possible. In this view, our dimensionality is not a random accident. It's a survival condition. Universes with other dimensional configurations might still exist, but they may be barren, brief, or utterly alien. There's another possibility, that dimensionality is a phase, just like water can be ice, liquid, or vapor depending on conditions. The structure of space itself may go through transitions. Perhaps in the ultra-hot, early moments of the universe, all dimensions were symmetrical and indistinct. As the universe cooled, some dimensions expanded, while others shrank. The breaking of dimensional symmetry could be similar to the symmetry breaking we discussed earlier, a spontaneous selection of one configuration over others, locking in the number of large dimensions we observe. This raises an extraordinary implication. Dimensions themselves may not be fixed properties of reality, but emergent behaviors. What we call space may be a fluid, a state, a pattern, one that can shift, bend or collapse under the right conditions. And that opens the door to ideas even more radical. Could we, in theory, access higher dimensions? If they exist, could we build machines to reach into them, extract energy from them, or even travel through them? Some theories of quantum gravity propose that black holes are connected by higher dimensional tunnels, or wormholes, stabilized by exotic physics. If these tunnels exist, they might allow information or even matter to shortcut across distances by briefly stepping into higher dimensional space. These are not established facts, but they are consistent with what our mathematics allows. The question is whether nature makes use of those possibilities. There's also the tantalizing thought that consciousness itself may be sensitive to higher dimensions, not in a magical or mystical way, but as a property of how complex systems interact with the fabric of reality. If space is more than three-dimensional, and if the brain's electrical and quantum processes interact with that space in subtle ways, then the architecture of thought could be influenced by geometries we cannot perceive. Again, this is speculative, but it hints at how deeply dimensionality could shape even our experience of being. And what about the end of the universe? If space-time is a fluid, and dimensions can emerge or disappear, then perhaps the universe is not evolving in space, but evolving as space. In this view, dimensional expansion might still be happening slowly, silently, right now. Perhaps new dimensions are forming in pockets of the cosmos, unnoticed. Or perhaps at some future threshold, a new dimension could awaken, stretching the universe into a higher reality, forever changing the laws of physics. This leads to the profound realization that we may never fully grasp the universe if we stay confined to our three-dimensional lens. Everything we measure, everything we model, is based on assumptions of space as a 3D canvas. But what if that canvas is folded? What if it loops back on itself, or hides surfaces beyond our reach? Mathematically, higher dimensions are not exotic, they're ordinary. Engineers already use multi-dimensional space to design data systems, visualize relationships, and model physics. The hard part is translating that math into observation, to find a signature, a crack in the illusion, a whisper from the extra dimensions hidden just beyond our fingertips. We may someday detect their influence through gravitational waves, cosmic background patterns, or quantum fluctuations. We may build detectors sensitive enough to notice how gravity bends in unexpected ways. Or we may never detect them directly, and still know they're there, because they complete the picture, solve the equations, make the universe coherent. So perhaps the most mind-bending realization is this: the universe might not be what we see, or even what we can see. It might be a projection, a cross-section, a membrane in a higher world. We are fish in a two-dimensional pond, glimpsing only shadows of the deep ocean beyond. And yet, even in our limitations, we have found ways to imagine, to model, to reach across dimensions we can't touch, toward a cosmos vaster than space and stranger than time. Chapter 19: The Arrow of Time. Why does time only flow forward? You can break a glass, but you can't unbreak it. You grow older, not younger. Memories form in one direction. The past is known, the future is unknown. But the laws of physics, they don't care. At the deepest level, the equations that describe our universe, the motion of particles, the structure of atoms, even the curves of space-time, are time-symmetric. They work just as well in reverse. There is no preferred direction in time according to the mathematics. If you filmed a planet orbiting a star and played the video backward, nothing in the equations would object. And yet, we feel time as a one-way street, forward, unstoppable, irreversible. This one-way flow is called the arrow of time, and understanding it may unlock the deepest mysteries of the cosmos, including where the universe came from, where it's going, and whether reality is fundamentally deterministic or ruled by chaos. The most common explanation for the arrow of time is entropy, the measure of disorder or randomness in a system. According to the second law of thermodynamics, in an isolated system, entropy always increases. Ice melts, buildings crumble, smoke disperses. This statistical tendency gives time its direction. It's more probable for systems to move from order to disorder than the reverse. A shattered glass contains more ways to be broken than to be whole. But this raises a profound question. If entropy increases over time, then why did the universe begin in a low entropy state? Why was the early universe so smooth, so ordered, so remarkably balanced? That's not the expected condition of a randomly configured system. It's as if a vast deck of cards began the game already sorted. The real puzzle isn't why time moves forward. It's why the initial state allowed that motion to even begin. Some physicists suggest that the Big Bang set the arrow of time. At that moment, the universe had minimal entropy, with energy and matter distributed almost perfectly. As the universe expanded, gravitational clumping increased entropy, allowing stars and galaxies to form, while still obeying the second law. In this view, the arrow of time is tied to the expansion of the universe. As space grows, entropy increases, the past is smooth, the future is messy. Others propose that the arrow of time is not fundamental, but emergent, a macroscopic illusion, much like temperature. Just as individual molecules don't have a temperature, but large groups of them do, perhaps time's arrow only appears when many particles interact in complex systems. On the level of quantum fields or individual events, time might be symmetrical, but when billions of particles collide, probability ensures a one-way direction. Still, the mystery deepens when we consider quantum mechanics. In quantum theory, the evolution of a system is time reversible, except when a measurement occurs. That's when the wave function collapses, and the system picks a definite state. Before measurement, particles exist in superpositions, blurred possibilities. Afterward, they lock into facts. This collapse appears to be irreversible, but what causes it? Is it observation, consciousness, decoherence with the environment? And why does it only go one way? One idea is that entropy plays a role here too. As a system interacts with its environment, entanglement spreads. The number of possible microstates grows, locking the system into a specific outcome, and increasing overall entropy. In this view, the arrow of time is connected to the spread of quantum information, the loss of coherence, as systems become entangled with their surroundings. There are more radical proposals as well. Some cosmologists argue that time may not be fundamental at all. Instead, it might be an emergent property of more basic relationships, such as change, causality or information flow. In these models, time is not a thing that flows, but a bookkeeping system for ordering events. In the deep fabric of quantum gravity or string theory, time may not exist in the traditional sense, only correlations between events, only relative configuration. And yet, even if time is emergent, the arrow still persists. We remember the past, not the future. Eggs break, ashes don't reassemble, signals transmit forward. In a universe governed by time-symmetric laws, this asymmetry cries out for explanation. One extraordinary proposal is that the universe might have two arrows of time, one pointing forward and another pointing backward, originating from a central low-entropy event. In this model, the Big Bang was not the beginning of time, but the mid. On one side, entropy increases as time flows forward. Our universe, on the other side, time also flows forward, but in the opposite direction. Inhabitants of that mirror universe would see themselves moving from past to future, just as we do, but their future would be our past. This symmetric time model restores balance to the equations. It explains the low entropy beginning as a boundary condition, not an unnatural fluke, and it opens the door to the idea that our direction of time is not unique. Somewhere else, time flows differently, not because the laws differ, but because the arrow chose another path. We might even ask whether free will and consciousness depend on the arrow of time. If our thoughts are the result of neural firings, and those firings depend on cause and effect, then reversing the arrow might reverse perception itself. Could a being exist in a reverse time universe and still think, choose, remember, or is the one-way flow of time essential to identity? Even in biology, time's arrow leaves its mark. Organisms age, memories form, evolution proceeds in steps that can't be undone. DNA records history, not prophecy. The metabolism of life, the growth of cells, the death of systems, all proceed in a forward march, bound by entropy's command. And then there are black holes, the most extreme expressions of time's grip. As matter falls inward, time dilates, slows, stretches. At the event horizon, time nearly halts. Inside, it may cease entirely, or loop, or branch. The singularity is not just a place where space ends, but where time breaks. Hawking once proposed that at the edge of a black hole, Information is not lost but smeared across the surface. The holographic principle. If that's true, then perhaps time too is encoded not inside things, but on the surfaces that define them. A strange thought, that time is a shadow cast by geometry. And what of the end of time? If the universe keeps expanding, stars will burn out, galaxies will drift apart, and eventually the cosmos will reach heat death, a state of maximum entropy where no more work can be done, no structure, no memory, just uniform energy spread thin across the void. In that final equilibrium, the arrow of time would fade, events would cease, history would end, a stillness beyond decay, or perhaps the cycle will begin again. Some theories suggest that after heat death, quantum fluctuations could spawn new pockets of low entropy, birthing new arrows of time, new universes, new histories. In this view, time is not linear but cyclical, forever resetting itself through cosmic rebirth. So what is the arrow of time? Is it entropy, causality, memory, choice, a mere statistical trend, or a deep metaphysical truth? We don't know, but we do know this. Something gave time a direction, something defined a before and after, and that something still rules our every moment. We are passengers on the arrow, moving forward whether we wish to or not. We remember the past, we dream of the future, and we live, always, in the now, the razor's edge of entropy's unfolding. Chapter 20. Non-locality. How distant particles know each other's secrets. Two particles are created in a single event. They spin off in opposite directions, miles, even light years apart. Yet, the moment one is measured, the other instantly responds. No signal is sent, no message travels through space, but somehow, they remain connected, as if space itself doesn't matter. This is not fantasy. It's a phenomenon known as quantum entanglement, and it challenges everything we think we know about locality, causality, and the structure of reality. In classical physics, information is local. An object can only influence another through some kind of interaction. A push, a pull, a signal, and nothing travels faster than light. These principles define the boundaries of causality. They tell us that space separates events, that distance insulates cause from effect, but entanglement defies this boundary. When two quantum particles become entangled, their properties become correlated in a very specific way. If one is measured and found to have spin up, the other will instantly be spin down, even if they're separated by light years. This isn't due to hidden variables or unseen connections. It's a direct consequence of how quantum states work. The system doesn't contain two separate particles but one unified state stretched across space. Einstein famously called this spooky action at a distance. He couldn't accept that reality allowed such instantaneous connections. In his view, there must be some deeper, hidden mechanism, local variables that determined the outcomes in advance. But experiments have shown otherwise. Starting in the 1970s, physicist John Bell formulated a mathematical inequality that tested whether quantum mechanics could be explained by local hidden variables. The result, known as Bell's theorem, showed that no local theory could reproduce all the predictions of quantum mechanics. If entanglement behaves as quantum theory says it does, then reality must be non-local. And over the decades, dozens of experiments have confirmed this. Most famously, Alain Aspect's experiments in the 1980s, and more recently, high-precision loophole-free tests, have demonstrated that entangled particles really do behave in a way that defies local explanation. When one particle is measured, the other reflects that result instantly, regardless of distance. But this doesn't mean information travels faster than light. That would violate relativity. In fact, no usable signal can be sent through entanglement alone. What's spooky is not communication, but correlation. It's as if the particles share a fate, a common destiny, written into their joint state. Until you measure one, the system is in a superposition. But once a choice is made, both outcomes fall into place, as if the universe remembers their origin. So what does this mean for the nature of space? If entangled particles remain connected across vast distances, then perhaps space itself is not fundamental. The separation we perceive may be an illusion, a useful map, but not the territory. In this view, the universe is not built out of points in space, but out of relationships, patterns of information, woven across a deeper reality. This idea aligns with some interpretations of quantum mechanics, such as relational quantum theory, which says that properties only exist in relation to other systems. There is no absolute position or momentum, only the information shared between systems. If this is true, then entanglement is not a glitch, but a clue. A glimpse into a world where connections matter more than locations. Other physicists go even further. In emergent space-time theories, space and time themselves may arise from entanglement. According to this view, the smooth geometry of the cosmos is not fundamental, but emerges from a vast network of quantum correlations. Imagine a web where each node represents a quantum system, and each edge is an entangled link. The structure of that web gives rise to the dimensions we experience. One key proposal in this area is called ER-EPR, a conjecture that links two very different ideas. ER refers to Einstein-Rosen bridges, or wormholes. EPR refers to Einstein-Podolsky-Rosen pairs, entangled particles. The conjecture suggests that every entangled pair is connected by a wormhole, a non-traversable tunnel, in space-time, not a passage for travel, but a mathematical bridge. If this is true, then the fabric of the universe is stitched together by entanglement. Wormholes are not science fiction oddities, but the architecture of space itself. This would mean that space is not a backdrop, but a construct, built from the threads of entanglement. The more entangled two systems are, the closer they appear in emergent space. The less entangled, the farther apart. Distance becomes a measure of quantum connectivity, not physical separation. This also has implications for black holes, and information falls into a black hole. Where does it go? Hawking once believed it was lost forever, breaking unitarity. But newer theories suggest that information may be encoded in Hawking radiation, quantum particles emitted at the event horizon. And if entanglement connects the inside of the black hole to the outside, then perhaps the lost information is preserved, just scrambled in a form we don't yet understand. In this way, non-locality becomes not a problem but a principle. It preserves information, it unifies space, it may even underpin consciousness. Some scientists speculate that quantum coherence in the brain, or in biological systems more generally, may depend on non-local correlations. While these ideas remain controversial, they hint at the possibility that our own thoughts and awareness might be influenced by patterns beyond locality, shaped not by proximity, but by entangled meaning. And still, non-locality forces us to ask what is real. If properties don't exist until measured, if correlations transcend space, if outcomes are linked regardless of distance, then our classical view of the world must be incomplete. Reality is not made of separate objects in isolated places. It is a unified field of potential, actualized only through interaction. In the many worlds interpretation, entanglement is even more dramatic. Every measurement splits the universe into branches, each reflecting a different outcome. Entangled particles don't choose a state, they manifest all states in separate realities. Correlation is preserved, because the branching respects entanglement. The outcome you see is mirrored by the version of the other particle in your branch. In this view, non-locality doesn't break space, it multiplies worlds. Of course, no interpretation has been definitively proven. Quantum mechanics works, but what it means remains open. What's certain is that entanglement is real, and non-locality is baked into the structure of the universe. We can test it, we can build quantum computers based on it, we can encrypt messages using quantum key distribution, which guarantees security through the impossibility of copying entangled states. These are not theories anymore, they are technologies. So what began as a spooky idea, a ghost in the math, has become a cornerstone of modern science. Non-locality is not an anomaly, it is a window into the deep structure of reality, and it suggests that the universe is not made of parts, but of connection. That identity is relational, that cause and effect are subtler than lines on a timeline, that space is not a void, but a veil, thin, shimmering, and easily pierced by the threads of entanglement. In the end, the greatest mystery may not be how distant particles affect each other, but how deeply everything is entangled. Not just particles, not just fields, but stars, galaxies, minds, time, all intertwined in a cosmic dance that transcends space, refusing to be broken, and echoing the first spark of the cosmos, when all was one. Chapter 21. Closed time-like curves. Can time loops exist in reality? Imagine traveling into the past, not metaphorically, not through memory, but literally, moving backward through time, and arriving at a moment before you began the journey. Now imagine doing it over and over again, looping through time like a groove in a record. This is the concept of a closed time-like curve, or CTC, a solution to Einstein's equations in general relativity. that under the right conditions, permits a trajectory through space-time that loops back on itself, a path through the fabric of the universe where time is curved so completely that a traveler returns to their own past. It sounds like science fiction, and in many ways it still is. But mathematically, closed time-like curves are allowed by general relativity, and not forbidden by the equations that govern the universe. That alone makes them fascinating and deeply unsettling. The first serious discussion of such loops came from Kurt Gödel, the famed logician, in 1949. He discovered a solution to Einstein's field equations that described a rotating universe, one in which time could, in principle, curve back on itself. In Gödel's universe, an object following a specific path could loop into its own past. Of course, we don't live in a universe like Gödel's. The cosmos we inhabit isn't rotating in that specific way. But his insight was revolutionary. It showed that Einstein's theory, the same one that explains black holes and the Big Bang, could accommodate time loops, that space and time under certain circumstances bend so far they reconnect. Other solutions followed. The Tipler cylinder imagined an infinitely long, rapidly spinning object, whose rotation could drag space-time around it into loops. The Van Stockum dust model proposed similar curves around rotating matter, and perhaps most famously, Kip Thorne and colleagues investigated whether traversable wormholes could serve as time machines. If one mouth of a wormhole is accelerated to near light speed and then returned, relativity predicts time dilation. The accelerated mouth ages less. If both mouths remain connected, the result is a time difference between their openings. Travel through the wormhole becomes travel through time. You enter one mouth in the future, exit the other in the past. The loop is closed. You've completed a circuit not through space but through history. This raises profound questions. What happens if you kill your grandfather, or warn your past self of the future? These are the infamous time travel paradoxes, logical contradictions that emerge when cause loops into effect. To resolve these paradoxes, physicists have proposed several frameworks. One is the Novikov self-consistency principle, which states that events along a closed time-like curve are constrained to be self-consistent. In other words, whatever you do in the past must be compatible with the present you came from. If you attempt to prevent your birth, something will intervene to stop you. Free will in this framework is limited. The timeline is like a film reel, fixed, unchangeable, looping eternally. Another approach is many worlds. Here, going back in time doesn't affect your own timeline, but spawns a new branch of the multiverse. You don't prevent your own birth. You create a new universe where you were never born. This resolves paradoxes by divorcing cause and effect across different branches of reality. And then there are chronology protection conjectures, most notably proposed by Stephen Hawking. He argued that nature forbids time travel on macroscopic scales, that quantum effects near the formation of a closed time-like curve would destroy it, like a cosmic firewall. This idea suggests that while time loops are permitted by classical equations, they're prevented by quantum mechanics. Time, in this view, protects itself. But these ideas remain speculative. No one has ever created a closed time-like curve. We don't even know if the necessary conditions could ever arise in nature, and many of the solutions, like infinitely long cylinders or perfectly stable wormholes, may be physically impossible. Still, the mathematics won't go away. Closed time-like curves appear in many proposed theories of quantum gravity, string theory, and even black hole interiors. In certain configurations of space-time, especially those with exotic matter with negative energy density, time loops remain theoretically viable. Negative energy may sound fictional, but it's not entirely. The Casimir effect, which we discussed earlier, creates regions with negative energy density between metal plates. Some theorists argue that with enough negative energy, you could stabilize a wormhole or prevent a loop from collapsing. But the energy requirements are colossal, beyond anything humanity can produce. If CTCs did exist, what would it be like to travel one? Would your memory remain intact? Would the loop be instantaneous, or stretched across years? Could you enter and exit at will, or would you be trapped, reliving the same events in a self-reinforcing cycle? Some models suggest that consciousness would become looped too. Your thoughts, choices, even awareness might circle endlessly, like a song stuck on repeat. Other models suggest a subtle leakage, tiny deviations that, over many loops, could produce instability. Perhaps the loop isn't perfect, perhaps it frayed. There are also ideas from quantum computing that use time loops in bizarre ways. In theory, Closed time-like curves could allow certain calculations to be completed far faster than with conventional machines. If an answer can be sent back in time to an earlier step, the computation becomes instantaneous, a concept called post-selected computation. But again, this remains purely theoretical. In recent years, researchers have explored whether quantum entanglement can mimic the behavior of CTCs by creating entangled states that evolve in carefully controlled ways. Some simulations suggest the behavior of particles traveling along loops, resolving their own past interactions. It's not time travel, but it's close. Philosophically, CTCs force us to re-examine causality. In everyday life, causes precede effects, but in a time loop, cause and effect become entangled. An action may be both the origin and the result of itself. This challenges the foundations of logic, agency, and identity. If you are influenced by your future self, are you the author of your own actions? Some philosophers argue that time loops dissolve the concept of first causes. Everything becomes part of a loop, with no clear beginning or end. This recursive structure may sound paradoxical, but it's common in mathematics. Think of recursive functions, or Mobius strips. Perhaps time is not a line, but a spiral. Not an arrow, but a loop. In ancient mythologies, time was often cyclical. Many traditions, from Hindu cosmology to the Mayan calendar, imagined the universe as a sequence of recurring ages, births, deaths, and rebirths. These were not metaphorical. They reflected a deep intuition that time might turn in on itself. Modern science is now catching up. We no longer dismiss time loops as fantasy. We explore them as possibilities. We ask, if the universe allows loops in space, why not in time? But perhaps the real question is not can time loops exist, but should they? Do they preserve coherence or break it? Do they enhance understanding or dissolve it into paradox? As we continue to probe the frontiers of quantum gravity and space-time, we may discover whether loops are a curiosity or a core feature of reality. Until then, closed time-like curves remain one of the strangest, most mind-bending ideas in all of physics, not merely because they offer time travel, but because they reveal how fragile our notions of past, present, and future really are. We walk forward through time, but the path may curve, and somewhere ahead, or behind, we may meet ourselves. Chapter 22. Mathematical Universes. What if everything is just math? What if the universe isn't made of particles, fields, or strings, but numbers? What if the true substance of reality isn't physical at all, but mathematical? No atoms, no quarks, just pure structure, just logic, just math. This idea may sound extreme, even abstract, but it's gaining ground among physicists and philosophers alike. Known as the mathematical universe hypothesis, it suggests that everything we observe, from electrons to galaxies, from consciousness to causality, emerges from an underlying mathematical structure. The universe is not described by math. The universe is math. At first glance, this seems like a poetic metaphor. After all, physics has always used mathematics as a language to describe the natural world. Newton's laws, Maxwell's equations, Einstein's field equations, all elegant expressions of nature's order. But what if this is more than a tool? What if it's a clue? Mathematics, in this view, is not a human invention. It's a discovery, a pre-existing reality that we uncover, like archaeologists digging through sand. When we find that equations describe gravity or that constants like pi and e appear in nature, we're not imposing patterns, we're revealing the structure of existence itself. This hypothesis is championed most famously by physicist Max Tegmark, who argues that any mathematical structure that is self-consistent exists physically, not as a metaphor, not as a model, but as a real universe. Ours is just one among countless mathematical structures, selected not by divine preference, but by compatibility with self-awareness. According to this view, reality doesn't require a substrate. There's no need for a stage made of energy or matter. The laws themselves are enough. If a mathematical structure contains consistent relations, it can host observers, and once those observers evolve, they will perceive their structure as physical. It's a radical inversion of our usual thinking. We often imagine math as subordinate to matter, equations describing particles, but here it's flipped. Particles are manifestations of equations, mass, charge, spin, all properties derived from symmetries, patterns, algebraic relationships. We are not made of things. We are made of rules. To support this, Consider how much of modern physics already behaves this way. Particles in the Standard Model are classified not by what they're made of, but by how they transform under mathematical groups. A quark is not a tiny dot of substance, it's a representation of symmetry. Even space and time, once thought to be the background of physics, are now described as emergent from information and geometry. Take quantum mechanics. The state of a system is described by a vector in a Hilbert space, a purely mathematical object. Its evolution is governed by operators and probability amplitudes. Nowhere in the equations is there mention of realness, only structure or general relativity, where gravity is not a force, but the curvature of a four-dimensional manifold. Space-time isn't a thing, but a geometric solution to a set of equations. In both cases, the math doesn't just describe the behavior of the universe, it is the behavior. If we push this idea further, we reach a stunning implication. Every consistent mathematical structure is a universe. Somewhere, in the vast abstract space of mathematical possibility, lies a structure where the constants are different, the laws are strange, and logic itself may be unfamiliar. These are not fictions. They exist, not in our space, but in the realm of logic, as real to their inhabitants as ours is to us. But how can we know this? How do we verify a universe we can't see? In a sense, we already do. When we simulate physics on a computer, when we model black holes, weather systems, or atomic interactions, we're creating simplified mathematical universes. These systems obey their own laws, evolve with their own causality, and sometimes give rise to emergent behavior. They're not conscious, but they are real, within their frameworks. This leads to the idea that consciousness itself might emerge from certain mathematical structures. If a configuration of rules supports self-awareness, then observers within that structure will perceive themselves as alive, even if the structure is entirely abstract. In this view, we are not accidental molecules, we are self-aware substructures of a vast mathematical form. Critics argue this is metaphysical overreach, that just because a mathematical model is consistent doesn't mean it exists. But proponents counter that there's no meaningful distinction between a physical reality and a perfectly consistent structure that gives rise to perception. From the inside, there's no way to tell the difference. This also explains why the universe is comprehensible, why math works, why the laws of nature can be written on a chalkboard. If the universe were not mathematical, there would be no reason for equations to govern it. But if it is math, then its order is not imposed, it's inevitable. And it raises a strange kind of existential question. If every mathematical structure exists, then so do all possible realities. In some, the speed of light is different. In others, gravity is repulsive. Somewhere, there is a universe where you never existed, and another where you always have. This is different from the many worlds of quantum mechanics. It's deeper, broader. Not every branch of a wave function, but every equation, every topology, every consistent axiom system. The level 4 multiverse, as Tegmark calls it, a space of pure math, where reality is just one structure among an infinite sea of logic. If this is true, then the question of why this universe becomes meaningless. There is no reason. We simply find ourselves in one of the structures compatible with self-awareness. In others, nothing evolves, no minds arise, no questions are asked, but wherever a structure allows thought, that thought happens. So does this mean we live in a simulation? Not necessarily, though the idea shares some similarities. The simulation implies a designer, a programmer, an external platform. The mathematical universe hypothesis requires no such agent. The structure exists in and of itself. It is not running on anything. It's simply. Still, the parallels are striking. Just as a video game world is governed by underlying code, our universe may be governed by immutable rules. Just as digital characters move through simulated physics, we move through equations. The difference is that our processor is not a machine, it's pure mathematics. And in that sense we may already be immortal, not our bodies or memories, but the pattern of our structure. Every thought we have, every experience, every moment of self-awareness, all encoded in the logic of our universe, and that logic, once instantiated, is eternal, not in time, but in truth. So the next time you balance an equation, trace a geometric curve, or contemplate a fractal, consider this. You may be glimpsing the architecture of existence, not a description of reality, but reality itself. When a mathematical insight clicks, it's not just in your mind, it's a resonance with the deep logic of the universe. We often seek the meaning of life in stories, emotions, or mysteries. But what if meaning is structure? What if beauty, truth, and consciousness are not separate from equations, but expressions of them? The universe doesn't have to mean something in the poetic sense. It can simply be, and what it is math. Chapter 23. Simulated Reality. Could we be living inside a code? How do you know you're real? Not in the philosophical sense, not in the Descartes I think therefore I am way, but literally, how do you know that the world around you, the ground beneath your feet, the sky above your head, the people you talk to, isn't part of a vast simulation? It's an idea that sounds like science fiction, and yet it has become one of the most discussed, debated, and strangely plausible theories in modern cosmology and philosophy. The simulation hypothesis, popularized by thinkers like Nick Bostrom, Elon Musk, and Neil deGrasse Tyson. The simulation argument proposes a mind-bending possibility that we are not the base reality, but rather digital entities living in a computational universe created by a more advanced civilization, a world made not of atoms but of bits. To understand why this idea is taken seriously, we need to examine the core logic of the argument. Bostrom's trilemma lays it out in three options. Either 1. All civilizations at our level of development go extinct before reaching the ability to simulate conscious beings. 2. Advanced civilizations can simulate minds, but choose not to for ethical or other reasons. Or 3. They do run such simulations, and we are most likely living in one. Why is the third option so compelling? Because if such simulations are possible, and civilizations do run them, then the number of simulated beings would vastly outnumber real ones. Just as a single computer can simulate thousands or millions of agents in a virtual world, a post-human civilization could simulate entire histories, planets, or even universes. Statistically, it becomes more likely that you are one of those simulations rather than one of the few beings living in base reality. Let that settle in. If simulations are cheap and reality is rare, then being simulated is the default condition, not the exception. Your world, your memories, your experiences, your identity, could all be code. So is there any evidence? Surprisingly, some scientists have proposed tests. One idea is that if space is a simulation, it might be discretized, like pixels in an image or voxels in a game. Instead of being continuous, space-time would be quantized into a computational grid. If this were true, there might be a resolution limit, a smallest possible length, like the Planck length, and a highest possible energy, like a simulation's frame rate cap. We might detect this in high-energy particle collisions, where behavior suddenly deviates from prediction, suggesting a grid-like limit. Other theories point to the fine-tuning of the universe, the idea that physical constants are improbably precise to allow life, gravity, electromagnetism, the strong and weak nuclear forces, all delicately balanced. If any were slightly different, atoms wouldn't form, stars wouldn't ignite, chemistry would fail. This uncanny precision might suggest intentional design or programming. Even quantum weirdness, like wave function collapse, non-locality and probability could be seen as shortcuts in a simulation. Why compute every outcome in advance when you can calculate only when observed? Just as a video game only renders what's on screen. And what about consciousness? If our minds can be simulated, if neurons can be modeled, if awareness can emerge from patterns, then our subjective sense of reality could easily be replicated. Your inner monologue, your feelings, all part of the program. Not fake, just digital. To many this is terrifying, but to others, it's liberating. Because if we are simulations, it doesn't diminish our existence, it just shifts the foundation. We are still conscious, still thinking, still experiencing. What changes is where we sit in the hierarchy of realities. Let's explore how such a simulation might be built. Imagine a civilization millions of years more advanced than us. They have the ability to simulate universes, not just environments but entire laws of physics. They don't build computers out of silicon, but perhaps from quantum fields, black holes, or even strings of energy. Their simulations are indistinguishable from base reality, because to the agents within them, the code is reality. Now imagine those simulations running their own simulations, nested layers of reality, universes within universes, a cascade of virtual minds, each believing it is real, each unaware of the level above. In such a framework, base reality might be vanishingly rare, a solitary point at the top of a pyramid of simulations. But who are the simulators? Are they alien scientists running experiments, historians reconstructing ancient worlds, artists crafting digital dreams, or are they us? Future versions of humanity, simulating their ancestors for research, entertainment, or nostalgia? And if they are watching, can we communicate with them? Some thinkers have proposed sending messages into the simulation trying to catch the attention of the programmers. Others argue that if the simulators are indifferent or unaware of us, then we may be completely isolated, just like characters in a video game, unaware of the player's existence. But there may be glitches, moments when the simulation breaks down, déjà vu, quantum randomness, time anomalies, Mandela effects, collective false memories that suggest the past was overwritten. Some people see these as evidence of edits, bugs, or version shifts, like the world is being patched while we live in it. Of course, none of this is proof. The simulation hypothesis is, at present, unfalsifiable. You can't prove or disprove it from inside. Just like a character in a novel can't verify the existence of the author. Still, the idea continues to captivate. Because it touches something primal, the question of what is real. It forces us to consider that perception and existence might be separable. That being conscious does not require being physical. That realness is a property of experience, not material. And it echoes ancient ideas, Plato's cave, Descartes' demon, Buddhist dreams. The notion that what we call the world is just a projection, a shadow of something deeper. If we are simulations, does that mean morality is meaningless? Not at all. In fact, it may make morality more essential. Because the simulators might be observing not what we build, but how we behave. We might be judged, not by our knowledge but by our character, or perhaps morality is intrinsic, a pattern that emerges in all conscious systems, no matter the substrate. Whether we are carbon or code, kindness and cruelty still matter, love still matters, suffering still matters. So what do we do with this idea? Do we try to break the simulation, find the source code, hack the matrix, or do we accept it and live meaningfully within it? Perhaps the truth is this: whether we are real, simulated, or something else entirely, we are here, we are experiencing, and that is enough. Because if the universe is a simulation, then we are the rendering, the output of equations, logic, purpose. And if not, then we are atoms, stars, evolution, entropy, just as wondrous, just as mysterious. Either way, the mystery remains, and so does the beauty. Chapter 24: Hyperdimensions. Could reality be bigger than we imagine? How many dimensions are there? It's a question that seems simple, even childish. We grow up thinking in 3 dimensions: height, width, and depth, a box, a room, a planet. Everything we touch seems to exist in these spatial terms. Add time, and we reach 4. The dimensions of space-time as Einstein described it. But what if that's just the beginning? What if reality has more dimensions, not metaphorically but physically, dimensions curled up, hidden, folded into the fabric of the universe in ways we can't directly perceive, real dimensions just as valid as the ones we move through, but utterly alien to our senses? Welcome to the world of hyperdimensions, where the number of dimensions isn't limited to what we can observe, but expands into the very structure of existence itself. In the early 20th century, a German mathematician named Theodor Kaluza proposed an astonishing idea. What if gravity and electromagnetism could be unified, not through new particles, but by adding an extra dimension of space? He showed that by extending Einstein's equations from 4 dimensions to 5, the resulting math naturally produced both gravity and Maxwell's equations for electromagnetism. In this 5-dimensional world, the forces weren't separate, they were simply shadows of geometry. Later, Oscar Klein suggested that this 5th dimension could be curled up, compactified into a tiny loop, so small we'd never notice it. Just as a tightrope looks like a line from afar but has a circular cross-section up close, the 5th dimension might be wrapped into a circle at every point in space. This became the foundation for theories of compactified dimensions, extra directions in space that are too small for us to detect directly, and it laid the groundwork for one of the most ambitious ideas in theoretical physics: string theory. String theory proposes that the fundamental particles of nature aren't points, but one-dimensional strings vibrating at different frequencies. The mode of vibration determines the type of particle, just like the note from a violin string depends on how it's played. But these strings can only vibrate properly in a space with 10 dimensions, 9 spatial, 1 temporal, or even 11, in the case of M-theory. Where are the extra dimensions? They're believed to be compactified, curled into complex shapes called Calabi-Yau manifolds, named after mathematicians Eugenio Calabi and Xing-Tung Yau. These aren't simple loops, but intricate six-dimensional geometries folded at every point in our three-dimensional space. The shape of these manifolds determines the properties of our universe, how particles interact, what forces exist, the constants of nature. All may be dictated by the geometry of dimensions we can't even see. If this sounds fantastical, remember that our eyes are not equipped to see electromagnetic waves beyond a narrow slice of the spectrum. Infrared, ultraviolet, X-rays. They're invisible until we build tools to detect them. The same may be true for dimensions. We may never experience them directly, but their effects could shape everything we do. Some experiments have attempted to find signs of extra dimensions. High-energy collisions at the Large Hadron Collider have searched for evidence of gravitons, hypothetical particles that might leak into other dimensions. If gravity is weaker than other forces, it could be because it's spread out across higher dimensions. There are also speculative ideas involving brane worlds. The notion that our universe is a three-dimensional brain floating in a higher dimensional bulk. We could be like soap bubbles in a vast hyperdimensional foam, each universe a membrane with its own physics. In such a model, other brains might pass close to ours, causing cosmic phenomena like the Big Bang. The origin of our universe could be a collision between higher dimensional objects, not an explosion from nothing, but an intersection in a larger space. Even dark matter might be explained this way. What if the missing mass in our universe is ordinary matter on a nearby brain? We wouldn't see its light, but we'd feel its gravity. And what about time? Could there be more than one temporal dimension? Some theories speculate that multiple timelines, or even multiple kinds of time, could exist in higher dimensional space. Not a single arrow, but a web of temporal directions. This could allow new kinds of causality, loops, or parallel dynamics beyond our comprehension. These ideas are deeply speculative, and yet higher dimensions are not just an invention of string theory. They appear in mathematics, topology, and even data science. In math, spaces with 5, 10, or 1,000 dimensions are common. Each dimension is just a degree of freedom, a direction in a space of possibilities. When you consider all the variables in a complex system, temperature, velocity, pressure, charge, spin, you're already dealing with a high-dimensional state space. In this sense, hyperdimensional thinking may be more natural than it seems. The brain itself may process information in a space far beyond 3 dimensions, folding memories, emotions, and sensory inputs into a mental topology we can't visualize but do experience. So why can't we see these extra dimensions? Because our senses evolved in a world where only 3 dimensions were relevant to survival. Just as a 2-dimensional being on a flat surface wouldn't perceive height, we may be blind to dimensions that lie perpendicular to all our perceptions. Still, their presence might be inferred. Just as shadows reveal hidden forms, so too might the laws of physics hint at deeper directions. If hyperdimensions exist, they could unlock a unified theory of all forces. They could explain the patterns of particles, the nature of dark matter, the origin of the universe. They could connect consciousness, computation, and cosmos in a single geometric whole. Or they could remain forever beyond our reach, a silent architecture holding the stage on which we play. And yet, there's something deeply human about imagining these extra dimensions. They speak to our intuition that the world is bigger than it appears, that there is more not just out there but in here, more reality, more structure, more mystery. In art, in music, in dreams, we often touch fragments of something vast, something that doesn't fit into a box. Perhaps that's hyperdimensional too, the emotional resonance of living in a world that is always more than we can see. Ultimately, hyperdimensions are not just about physics, they are about imagination. They ask us to stretch our minds beyond the familiar, to picture what can't be pictured, to trust that reality doesn't owe us clarity, only possibility. 3 dimensions? 4? 10? Maybe the number doesn't matter. Maybe what matters is the fact that we're still exploring, still curious, still peering into the shadows, looking for the edges of our cage. Chapter 25. The Ultimate Ensemble. Could every possibility be real? What if everything exists? Not just everything you've seen, not just everything that could happen in this universe, but literally every logically possible reality, all existing simultaneously, eternally, as part of one vast totality. This is the idea of the ultimate ensemble, a concept proposed by Max Tegmark, and it's among the most radical ideas in the philosophy of physics. According to this theory, All that exists, or could ever exist, is not limited to our universe, our timeline, or our set of physical laws. Instead, every possible mathematical structure exists, and each one corresponds to a real, physical universe. It's not a multiverse, it's something beyond even that. A plenitude of being. A total set of all possible realities, each one equally valid, each one equally real, whether it contains galaxies or none at all. In this view, reality is not something with boundaries, it is not shaped by constraints or governed by a singular set of equations. Instead, it is a vast mathematical library where every book, every pattern, every logically coherent set of rules manifests as a distinct, self-contained universe. Some of these universes resemble ours. They have space, time, energy, and matter. They follow physical laws we might recognize: gravity, electromagnetism, quantum mechanics. Perhaps they even contain life minds, civilizations. Others are stranger. Universes with 3 dimensions of time and 1 of space. Universes where cause follows effect backward. Universes governed not by probability, but by logic loops. Universes built entirely from information, or silence. And some are utterly alien structures we can't even begin to visualize. Their laws don't just differ in detail, they differ in form. In these places, perhaps nothing moves, or nothing can ever be known, or identity has no meaning. Yet, if their mathematical structure is consistent, they exist, just as validly as ours. Tegmark's bold claim is this: existence is not a special quality. It is simply being mathematically well defined. If a system of equations is coherent, it is. There is no need for a substrate, no need for material instantiation, no need for someone to observe or simulate it. Existence arises from consistency. This leads to a provocative consequence. Your universe is not special. It is not the center. It is not chosen. It is simply one of an infinity of consistent systems, one where self-aware beings happen to exist. From this perspective, asking why are we here becomes a kind of category error. We are here because we are in a structure that allows minds to arise. In all the other structures where minds do not arise, no one asks the question, no one wonders about being, because there is no one. This is sometimes called the anthropic ensemble, the idea that our existence filters the range of possible realities. We don't live in a universe that was made for us, we live in a universe we can live in. The rest are still there, we're just not inside them. It also means that for every version of you in this universe, the person sitting here reading or listening to these words, there are infinite others in infinite contexts. You, in a world where gravity is stronger. You in a world where light moves backward. You, in a world where this chapter ends differently. You that never existed at all. Not hypothetically. Actually. You may wonder, why believe this? Isn't it just speculation? A metaphysical indulgence? But the answer lies in the unreasonable effectiveness of mathematics. Why does math describe nature so well? Why does every discovery in physics, from the orbits of planets to the spin of electrons, fall neatly into mathematical structure? If math is the foundation of reality, then the ensemble follows naturally. There is no need for a realness filter, no need to separate the true structures from the false ones. All of them exist, and we, like all beings, simply find ourselves within the one that supports our kind of experience. This also solves the problem of fine-tuning. Why is the universe so delicately balanced? Why do constants fall into the narrow range that permits life? Because in the ensemble, every combination occurs. The majority produce sterile, chaotic, or empty realities. But in a few, in rare mathematical pockets, life blooms. And life, by definition, arises in those pockets. So how does this affect how we live? It can be overwhelming to think that we're just one flicker in a sea of endless realities, that our universe with all its drama, struggle, beauty and pain is just a data point in a boundless set. But there is also comfort in it. If every possible version of existence is real, then nothing is ever truly lost. Every good outcome plays out somewhere. Every noble act echoes in some corner of the ensemble. You, as you are now, are part of something unimaginably vast, not just this universe, or this planet, or this species, but the total tapestry of what can be. And that gives your existence a strange kind of inevitability, not that you were destined to be here, but that somewhere you had to be. This doesn't render your choices meaningless. In fact, it elevates them. Because every choice is a path through the ensemble. Every decision branches the pattern of what you become. And in the local context of your lived world, the one you feel, breathe, and remember, those choices are all that matter. The ultimate ensemble doesn't tell us how to live. It tells us how vast the context of living is. We are not the product of a singular story. We are a thread woven into a fabric of all stories. Each universe a stanza, each mind a rhyme, each question, including this one, just one of countless echoes in the structure of what is. So as we close this final chapter, let the scale of it all settle into you, let it humble you, and empower you. Because even though you are a brief moment in a fleeting universe, you are also the witness of that moment, the questioner, the experiencer, and in the ultimate ensemble, that may be the most profound existence of all.